In the vast theater of the cosmos, black holes have always been cast as monstrous endpoints, the final fate of collapsing stars, the bottomless maws of spacetime that devour matter, light, and even information. But what if that terrifying boundary between existence and oblivion could be crossed not by collapsing mass, but by light itself? What if, instead of a dying star, you simply had too much brilliance in one place? So much radiance, so much pure energy, that it bends reality the way a planet or a sun would, and then tears a hole straight through it? This is the eerie, almost poetic paradox at the heart of one of the most fascinating and lesser-known theoretical objects in physics, the Kugelblitz, a black hole made entirely of light. That's right, not born of matter, nor crushed remnants of dead stars, but born from focused radiation. A Kugelblitz is what happens when light, the very thing we associate with vision, illumination, and understanding, folds in on itself so tightly that it disappears into darkness. Not metaphorically, but literally. When photons, massless particles of energy, become so intensely concentrated that they trigger a gravitational collapse, you don't get a flash. You get a singularity. A black hole formed from light. But before we continue, subscribe to the channel so you don't miss out on any of these videos. To the everyday mind, this sounds impossible. After all, light is intangible. It doesn't have weight. It doesn't rest or settle. But at the heart of modern physics lies an important principle. Light has energy, and energy is equivalent to mass. Einstein's famous equation, E=mc², doesn't just imply that mass can be turned into energy. It also means that energy can bend spacetime just like mass. And when enough energy is compressed into a small enough region, it doesn't matter whether it came from matter or light. The result is gravitational collapse. The Kugelblitz is the embodiment of that idea. A black hole birthed not from death, but from intensity. But what does this really mean? In practical terms, a Kugelblitz would behave just like any other black hole. It would have an event horizon, a point of no return. It would warp spacetime, slow time around it, and consume anything that dares approach too closely. You could orbit it, fall into it, study its thermodynamics, and it would follow the same rules as a black hole born from a star. What makes it remarkable isn't what it does, but what it is. The mere idea challenges our assumptions. We're trained to associate gravity with mass, and mass with matter. But light has no rest mass. Photons zip through the universe at the speed of light, never stopping, never aging. And yet, under the right circumstances, if you were able to concentrate enough of them, billions of trillions, compressed into a fantastically small volume, they could warp the very structure of reality into a singularity. Into a place where space folds, time stops, and nothing escapes. It's not science fiction. It's science. Theoretical physics, born from general relativity, allows such a possibility. And though no Kugelblitz has ever been observed, the equations don't forbid it. In fact, they suggest that such an object could exist, and may even have existed, fleetingly, in the early universe. Imagine a flash of gamma radiation, born milliseconds after the Big Bang, focused enough, hot enough, and dense enough to collapse on itself. That would be a primordial Kugelblitz, a cosmic echo of creation forming a tear in the very fabric of the universe, not from collapse, but from creation's intensity itself. This flips our narrative about black holes on its head. They are no longer only endpoints of entropy and collapse. They might also be born from pure energetic concentration. The ultimate paradox: light, in overwhelming abundance, turning into darkness. A photon funeral where brightness itself becomes invisible. But perhaps most mind-bending of all, a Kugelblitz requires no matter at all. You don't need stars, planets, or dust. In theory, if a civilization advanced enough could generate and focus stupendous quantities of energy, even from lasers or radiation beams, it could create a black hole in a laboratory. A light-born singularity. That's more than just a science experiment. That's godlike engineering. And therein lies the strange appeal of the Kugelblitz. It's not just a concept of astrophysics. It's a mirror held up to the nature of reality itself. That energy, not just matter, can bend and break the rules of existence. That light, the most ethereal and elusive of phenomena, can collapse into something as absolute as a black hole. The term, Kugelblitz, sounds like something out of myth or folklore, mysterious, elemental, and primal. And in a way it is. In German, Kugelblitz literally means ball lightning, a name that conjures images of glowing orbs floating through the air, crackling with raw power, seething with mystery. Ball lightning is itself a puzzling and elusive atmospheric phenomenon, rare, unpredictable, and not fully understood even today. It often appears during thunderstorms as a glowing sphere of electricity that drifts through the air, hovers eerily, and then vanishes, sometimes with a violent pop. It's no coincidence that physicists borrowed this eerie, almost mythical term when trying to name one of the most exotic constructs ever conceived by general relativity. In choosing the name Kugelblitz, they weren't just invoking the raw spectacle of glowing spheres. They were tapping into the poetic symmetry of a phenomenon that appears luminous, spherical, untethered, and yet deeply powerful. A name that captures both the intensity and the strangeness of what it describes. The first known use of the term in a modern physics context can be traced to the mid-20th century, as physicists began probing the extremities of Einstein's equations. It was a time of atomic breakthroughs and a rapidly evolving understanding of how energy and mass are interchangeable. The idea arose, if light and radiation could be packed so densely into one space that they gravitationally collapsed, what would you get? You'd get a light bomb, of sorts. A photon implosion. A sphere of light so intense it tears through spacetime like a singularity. The parallels to ball lightning were both symbolic and visual, an intense, glowing ball that contains more power than anything around it, and is completely alien in behavior. But in this case, it's not a quirky weather event, it's a doorway into gravitational oblivion. By naming this theoretical object Kugelblitz, physicists wrap something deeply technical in a cloak of natural mystery. The name gives it personality, gravity, quite literally, and a bridge to our imagination. It helps to humanize the abstraction. Kugel, for a sphere. Blitz, for lightning. Together, a powerful collision of concepts, geometry and chaos, precision and violence, form and energy. There's a certain irony in the name, too. Ball lightning is ephemeral, here for a flash, gone in a moment, sometimes witnessed, often doubted. A Kugelblitz, by contrast, is the opposite. Once formed, it endures. It becomes eternal in a very real sense, thanks to the singularity at its core. The fleeting image of a glowing sphere is thus attached to one of the most permanent and inescapable structures in the universe, a black hole. A poetic inversion that deepens the intrigue. It's worth noting that the use of German terminology in physics is not unusual. From Schwarzschild radius to Einstein tensors, the German language has left a profound imprint on the lexicon of modern theoretical physics. In this case, though, the term Kugelblitz isn't just technical, it's evocative. It captures imagination. It hints at forbidden knowledge. It makes you wonder what it would look like to see such a thing, a sphere of pure radiance collapsing under its own weight, an explosion that goes inward instead of outward, a final flash that leads to eternal darkness. The name also subtly implies danger. The word blitz isn't just lightning, it's violent lightning, an attack, a shock, an unstoppable burst. In military history, blitzkrieg refers to lightning war, sudden, overwhelming force. A Kugelblitz, by its very nature, represents a kind of war on spacetime itself. A sudden and catastrophic folding of reality, initiated not by mass, but by the purest form of energy. It is an implosion without substance. A wound in the universe, carved by light. This is not just clever nomenclature. It's a framing device that shapes how we perceive the idea. Without it, the concept might be dismissed as a mere technicality of equations. With it, the Kugelblitz becomes something visceral, something haunting. A celestial contradiction, wrapped in the language of storms and spectacle. And like the elusive atmospheric phenomenon it's named after, the Kugelblitz remains a ghost on the edge of our understanding, never observed, only predicted. A name that carries both the mystery of nature and the precision of theory, illuminating just how much power can lie hidden in a single word. At the heart of the Kugelblitz concept lies one of the most revolutionary ideas in all of physics, an idea that reshaped our understanding of the universe, of matter, of time, and of reality itself. It begins with a deceptively simple equation, E = mc squared. When Albert Einstein first formulated this relationship in 1905, he wasn't thinking about black holes or radiant collapses. He was exploring the idea that mass and energy are fundamentally equivalent. In its simplest interpretation, the equation tells us that a tiny amount of mass can be converted into a tremendous amount of energy, since it's multiplied by the square of the speed of light, a colossal number. It also works in reverse. Energy has a mass equivalent. Even if something has no rest mass, if it carries energy, it behaves as if it has mass in certain circumstances. This is where photons, the particles of light, come in. Photons are massless. They have no rest mass, which means you can't put them on a scale and measure weight in the traditional sense. But photons do have energy, and as strange as it may sound, this means that they gravitate. They can be affected by gravity, as we know from the phenomenon of gravitational lensing, where light bends as it passes near massive bodies like stars or galaxies. But more surprisingly, and crucial to the Kugelblitz, is that light can also cause gravity. This counterintuitive idea comes from Einstein's theory of general relativity, which extended far beyond the familiar concepts of Newtonian physics. While Newton saw gravity as a force acting at a distance between masses, Einstein realized that gravity is actually the warping of spacetime itself. Matter and energy tell spacetime how to curve, and curved spacetime tells matter and energy how to move. So it's not just mass that bends spacetime. It's energy. Any form of energy. A moving object, a pulse of heat, a blast of radiation. They all have energy, and energy creates curvature in the fabric of the universe. The more energy, the more curvature. This means that a concentrated beam of light, if powerful enough, can warp spacetime just like a planet or a star would. And if that energy is focused into a small enough volume, it can cause such extreme curvature that a singularity forms. That's a Kugelblitz. A black hole born entirely from the energy of radiation. Einstein's equations don't discriminate. They don't require mass in the traditional sense to trigger gravitational collapse. They only care about energy and momentum. The stress-energy tensor, the mathematical entity that appears in the Einstein field equations, includes all types of energy, mass, radiation, pressure, even tension in a string. All of these contribute to the shape of spacetime. And so, the universe doesn't care whether gravity is coming from a collapsing iron core of a dying star, or a searing orb of pure gamma radiation compressed into a pinpoint. The result, if the critical threshold is met, is the same: spacetime folds inward. An event horizon forms. A black hole is born. This realization has profound implications. It blurs the line between matter and energy in the context of gravitation. It shows that the essence of a black hole is not the stuff it's made of, but the energy density it achieves. Whether you compress neutrons, atoms, or photons, if you can squeeze enough energy into a small enough region, you break spacetime the same way. One might think of light as weightless, harmless, even fragile. But general relativity says otherwise. In great enough quantity and density, light can become gravitationally violent. It can become destructive. Not by burning, not by radiating, but by collapsing the very arena in which everything else exists, spacetime itself. And here, Einstein's insights are breathtaking in scope. His field equations, which look so abstract and complex on paper, are capable of describing not just stars and galaxies, but also objects that seem to defy ordinary thinking, like a black hole made of light. These equations have the power to predict things we've never seen, but which the universe may well allow. The Kugelblitz is a perfect example. If light can generate gravity, and enough gravity can create a singularity, then the bridge between radiation and collapse is complete. Einstein may not have imagined the full implications of his work in this specific way, but the groundwork he laid makes the idea not just plausible, it makes it inevitable, at least in theory. And so, with a few lines of mathematics, the idea that gravity belongs only to mass is shattered. Light, in sufficient intensity, becomes just as capable of altering the geometry of the cosmos. From the tiniest photon to the mightiest laser pulse, energy is gravity. The universe obeys this rule without exception. This realization opens the door to all sorts of possibilities, some terrifying, some awe-inspiring. Because if light can collapse into a black hole, then the very tools we associate with illumination and knowledge might also lead us to the edge of cosmic darkness. Imagine standing in a vast, dark void, no sound, no matter, no stars, just emptiness. Now imagine unleashing a beam of light so intense, so overwhelmingly powerful, that it floods the darkness in every direction. Not just a flashlight or a searchlight, but something beyond even our most powerful lasers. A storm of photons, each massless on their own, racing at light speed. At first, it seems harmless. Light, after all, passes through things. It illuminates. It doesn't pile up. But here's where the rules of ordinary thinking begin to break. As the energy of the light beam increases, and the photons begin to crowd into an ever tighter volume of space, their collective presence starts to matter. Not because they're pushing against something, but because their energy density, the amount of energy confined in a given volume, is increasing. And with that, their gravitational influence grows. Not individually, but collectively, their energy begins to warp the space around them. Now keep squeezing them inward, more tightly, more violently. Focus that radiation using some hypothetical, perfectly reflective structure or a gravitational lens. Imagine compressing a trillion joules into a space the size of a subatomic particle. The photons are all still flying at light speed, yes, but their density becomes so extreme that spacetime begins to buckle. At some critical threshold, the outward momentum of the radiation becomes irrelevant compared to the inward pull of its own gravity. And then, collapse. Not a collapse like matter falling inward under its own weight. This is different. It's the geometry of spacetime itself falling in on itself, under the strain of too much energy. The region becomes so curved, so warped, that an event horizon forms, a spherical boundary beyond which no information can escape. Inside that horizon, all the energy, all the light, is trapped. The photons are still moving, still massless, still racing forward at the speed of light. But the very space therein has curved inward so completely that every direction leads inward. To an outside observer, this process would look strange. First, an unimaginable burst of radiation. Then, abruptly silence, as if the light disappeared. But in reality it hasn't vanished. It's simply been swallowed by its own gravitational pull. The region where the light once blazed now appears completely black. It doesn't reflect. It doesn't emit. It simply is. A black hole. This is what it means for light to collapse on itself. No solid matter, no atomic structure, no pressure from collapsing iron cores, just the raw intensity of radiation, so concentrated that it tears a hole in the universe. This theoretical process draws its logic straight from Einstein's general relativity. The key idea is that when the energy density within a region surpasses a critical threshold, known as the Tolman-Oppenheimer-Volkoff limit in the context of matter, but more broadly governed by the so-called Hooke conjecture, the region becomes a candidate for black hole formation. For photons, the critical density required is astronomically high, but it's not infinite. Which means that, in principle, the process is physically allowed. This is the astonishing part. A Kugelblitz doesn't break any laws of physics. It's not some wild violation of known principles. It's a direct consequence of combining Einstein's insight about energy and spacetime with the properties of massless particles like photons. The only reason we've never observed one is because the energy levels required are staggeringly beyond anything we can produce, for now. To create such a collapse, you need to focus as much energy as a star produces over its entire lifetime, into a space smaller than an atom. The challenge is not theoretical. It's practical. But if nature ever managed to produce such conditions, say, in the high-energy chaos of the early universe, then kugelblitzes could have formed naturally. If an advanced civilization ever harnessed energy on scales we currently can't fathom, they might manufacture them deliberately. And perhaps most bizarrely, a kugelblitz collapse is non-material. There is no substance to hold or touch. It's a singularity birthed not by mass, but by convergence. It's gravity without matter. It's like watching a screen fold into silence because it was too loud. The idea of light collapsing into darkness has an eerie dimension to it. It's the ultimate inversion of what light symbolizes: knowledge, clarity, presence. And yet, when concentrated beyond reason, light becomes paradoxical. Too much illumination, and it vanishes into the void. So how much energy would it actually take to create a kugelblitz? To answer that, we must first understand the central idea behind gravitational collapse: the energy density. Not just energy, but how tightly that energy is packed into space. If you want to bend spacetime enough to form a black hole, you don't just need a lot of energy. You need to concentrate it into a region small enough that its gravitational pull overwhelms any outward force. In the case of a kugelblitz, this means cramming pure radiation into a volume so tiny, and with such ferocity, that it essentially collapses under its own energetic gravity. Let's use the most familiar black holes we know as a baseline: stellar black holes. These form from massive stars at least a few times larger than our Sun. When the fuel of such a star runs out, and its internal pressure can no longer resist gravity, the core collapses into a singularity. The amount of mass involved in creating a black hole like this typically ranges from around 3 to tens of solar masses. In other words, more mass than the Sun itself. To generate a kugelblitz of similar mass, we wouldn't be using matter at all, we'd be using energy. But thanks to Einstein's equation, we can treat energy and mass as equivalent. According to E equals mc squared, one solar mass corresponds to roughly 1.8 times 10 joules of energy. That's a 1 followed by 47 zeros, a figure beyond human comprehension. For comparison, the entire energy output of the Sun, in all directions, every second, is about 3.8 times 10 superscript 2 joules. So, to accumulate one solar mass worth of energy, you'd have to bottle up every joule emitted by the Sun for about 150 million years, and then somehow focus it all into a tiny enough region to trigger gravitational collapse. That's the raw scale of what we're talking about. But maybe you don't need a full solar mass black hole. What if we aim lower? Even a tiny black hole, say, with the mass of Mount Everest, would still require unimaginable energy. Everest has a mass of about 10 superscript 1 kilograms, which translates to 9 times 10 superscript 3 superscript 1 joules of energy. That's still more energy than all human civilization has ever produced since its inception, by many, many orders of magnitude. And here's the kicker: it's not just about the amount of energy, but also about the size of the region it's compressed into. That's where the challenge becomes even more extreme. The Schwarzschild radius, the size of the event horizon, scales linearly with mass. A black hole with the mass of Mount Everest would have a radius of about 1.5 times 10 superscript 1 superscript 2 meters, smaller than an atom. So all that radiation would need to be packed into a space no bigger than a proton. Not just tightly packed, but perfectly focused, directed with absolute precision, and contained in a way that doesn't allow it to escape before collapsing. And that's where things get almost absurdly difficult. Unlike matter, radiation is naturally expansive. Photons are always moving at the speed of light. They don't want to stay in one place. They resist confinement not through pressure, but through constant outward motion. So the engineering task of holding them in, even for a fraction of a nanosecond, becomes one of the most impossible barriers we can imagine. It would require a mechanism or structure that can reflect, direct, or trap photons with zero loss. No known material can do this. No known force configuration has been proven to accomplish it. Unless gravity itself is used. In principle, one could imagine using gravitational lensing to redirect incoming beams toward a single point. An advanced civilization might create a massive shell of mirrors, not physical ones, but gravitational ones, that guide an enormous number of high-energy beams inward toward a central convergence. There, if the energy density builds fast enough, a kugelblitz could be born. This is what some theorists have called a photon bomb, not in the explosive sense, but in the idea of collapsing light to trigger black hole formation. The result is not destruction in the traditional sense, but rather the creation of an entirely new region of spacetime. A place that no information escapes. A prison built of brilliance. Even more speculative ideas suggest using gamma rays, the highest energy form of light, to achieve this goal. Gamma ray bursts, the most powerful explosions observed in the universe, emit more energy in a few seconds than the sun will in its entire 10 billion year life. If one could be artificially generated and then focused into a pinpoint, the result could be gravitational collapse via radiation alone. But that still only scratches the surface of what's required. The alignment, the timing, the synchronization of wavefronts, the lack of dispersion, all must be perfect. And the slightest imbalance would cause the photons to scatter rather than collapse. There's also an interesting implication. The smaller the black hole you want to create, the more extreme the energy density has to be. So paradoxically, tiny kugelblitzes are harder to create than massive ones. This is because the radius shrinks with mass, and that means the energy must be packed into an even tinier space. Creating a black hole the size of a proton requires compressing energy to levels so high they approach, or even exceed, the Planck scale, where our current physics begins to break down. And yet, despite all these unimaginable barriers, the theoretical path remains open. The universe says, yes, if you can bring this much energy into this small a space, a black hole will form. Whether it's matter or light, it doesn't matter. Spacetime responds only to the stress-energy tensor. Collapse doesn't care what's doing the collapsing. So the threshold for creating a kugelblitz is clear: gather an astronomical amount of energy, more than a star emits over eons, and crush it into a point so small it defies comprehension. If you can do that, you will have made light eat itself. You will have created a black hole not from matter, but from concentrated radiance. A sun's lifetime of brilliance, converted, focused, and made to disappear into the silence of a singularity. When we think of black holes, the default image is almost always one born from matter, the endgame of a massive star that lived a fiery life and died in catastrophic collapse. Stellar black holes dominate our astronomical observations and models. They form when a star many times the mass of our Sun exhausts its nuclear fuel. Without the outward pressure of fusion to counteract gravity, the core implodes, crushing matter down into an unimaginably dense point, a singularity, surrounded by an event horizon, the point of no return. But a kugelblitz upends this narrative. It doesn't arise from matter at all. It doesn't need hydrogen, helium, or even atoms. It doesn't go through a nuclear life cycle. There's no supernova, no iron core collapsing under its own weight. A kugelblitz forms from pure radiation, an overwhelming flood of light so concentrated that it creates a gravitational field strong enough to trap itself. So, what exactly are the differences between these two black hole types, one birthed by matter, the other by light? Let's begin with origin. A stellar black hole is born from mass. It comes from a star, a massive, burning cauldron of plasma held in delicate balance by nuclear fusion. Over millions or billions of years, it fuses elements in its core, generating light and pressure to keep gravity at bay. But eventually, when the star can no longer fuse elements into heavier ones, typically after reaching iron, which doesn't produce energy when fused, the internal pressure collapses. Gravity wins. In the aftermath, the outer layers may explode in a supernova, but the core is doomed. It shrinks under its own gravitational weight until it compresses into a point of infinite density. A black hole. A kugelblitz, by contrast, doesn't begin with a star. It doesn't begin with mass at all. It starts with energy. Specifically, energy in the form of electromagnetic radiation, typically envisioned as a burst of gamma rays or highly focused laser beams. The core difference here is that there is no physical object collapsing. Instead, there is only light. But thanks to general relativity, we know that energy can bend spacetime. When light is concentrated enough, its energy density can become so great that it curves spacetime to the same degree mass would. At a critical point, this curvature becomes extreme enough that the light traps itself, the same way a collapsing star does. It forms a singularity, complete with an event horizon. But instead of matter creating the trap, it's radiation folding in on itself. Next, we examine composition. At first glance, this seems like an easy distinction. One is made of matter, the other of light. But things are more complicated once a black hole has formed. Inside the event horizon, the concept of composition loses its ordinary meaning. Matter doesn't remain as atoms, protons, or electrons. Everything collapses into a singularity, a region where density becomes infinite, and the known laws of physics cease to function in their normal form. That means both stellar black holes and kugelblitzes are, ultimately, indistinguishable in their internal makeup, at least according to classical general relativity. Both contain a singularity, both are surrounded by an event horizon, and both eliminate any trace of what went into making them. The no-hair theorem of black holes asserts that black holes can be fully described by just three observable properties: mass, charge, and angular momentum. Not by what created them. So if we were observing a stellar black hole and a kugelblitz from outside, we would not be able to tell them apart by looking at them directly. There is no visual fingerprint that says, "This one came from a star," and "This one came from light." But this leads to another key point: formation dynamics. The way these black holes are formed leaves a very different footprint in terms of the environment they emerge in. A stellar black hole leaves behind remnants, neutron stars, heavy elements scattered into space, supernova shockwaves, magnetic fields, and often a surrounding accretion disk of leftover stellar matter spiraling inward. These features make stellar black holes easier to detect, because they interact with nearby matter in dramatic and luminous ways. A kugelblitz, however, may leave behind nothing at all. It could form in deep space from an isolated beam of gamma radiation, or in a futuristic lab under precise conditions. Once it forms, there may be no matter around to light it up, just the sudden appearance of a gravitational source with no visible cause. This makes it far harder to detect. It could be entirely invisible except for the gravitational effects it exerts on nearby objects, or the lensing of background light. Another important difference is in evaporation and lifespan. Both types of black holes are subject to Hawking radiation, the theoretical process by which black holes slowly lose mass and energy over time due to quantum effects near the event horizon. This means that all black holes will eventually evaporate, given enough time. But the rate of evaporation depends on the mass of the black hole. Smaller black holes emit more Hawking radiation and evaporate faster than large ones. In this regard, a kugelblitz might be created with a very small mass, perhaps even microscopic, depending on how much energy is used to form it. Such tiny black holes would evaporate quickly, potentially in fractions of a second. Stellar black holes, by contrast, are huge, stable, and would take far longer than the current age of the universe to evaporate completely. This opens up fascinating speculation. Could short-lived mini-kugelblitzes be created and detected in high-energy particle collisions or laser experiments? They would appear and vanish almost instantaneously, possibly emitting bursts of Hawking radiation as they die. If such events could be identified, they would not only confirm the existence of kugelblitzes, but also offer direct evidence of quantum gravity. There's also a subtle difference in thermodynamics. Because a kugelblitz is formed from radiation, it starts out hot, in a conceptual sense. The energy that went into making it was high-frequency, high-temperature electromagnetic radiation. But once it collapses into a black hole, that initial temperature doesn't matter. The resulting black hole has a temperature inversely proportional to its mass, the same rule that governs stellar black holes. However, if the kugelblitz is small, its temperature would be high, and it could emit radiation quickly, shrinking rapidly in a runaway process. This brings us to perhaps the most poetic distinction of all, the symbolism. A stellar black hole is death, the collapse of matter, the end of a star, the gravitational tombstone of a long-burning celestial body. It symbolizes decay, destruction, and the limits of matter. A kugelblitz, in contrast, is too much life. It is not a collapse due to exhaustion, but due to excess. It is brightness made so intense, so dense, so overwhelming, that it folds into itself and vanishes. It represents the paradox of overconcentration, the idea that brilliance can become blindness, that light can create darkness, that radiation can end in silence. In a cosmic sense, it's a reminder that extremes converge. Too little energy, and nothing happens. Too much, and you get gravitational implosion. Whether it's matter failing to sustain itself, or radiation trying to burn too brightly, both can lead to the same fate, the formation of a black hole. So ultimately, while the origin stories differ, matter versus energy, the end result is the same, a singularity wrapped in a horizon, governed by the same laws, indistinguishable in behavior, terrifying in implications. But knowing that one was born from light and the other from matter? That changes the story. It changes how we think about the universe. Because it means that even something as intangible as light, when focused and multiplied enough, becomes indistinguishable from gravity. And in the most literal way possible, light becomes darkness. When most people hear the word gravity, they instinctively think of weight, of things with mass, apples falling from trees, planets orbiting stars, or bodies being pulled toward the Earth. And that makes sense. In our everyday lives, gravity feels like a force that acts only on massive things. Light, on the other hand, doesn't seem to fit that picture at all. It's intangible. You can't hold it. You can't weigh it. It doesn't rest. It doesn't sit still. In the classical Newtonian view of the world, light and gravity would have nothing to do with each other. But modern physics tells a different story. In Einstein's theory of general relativity, gravity is not a force between masses, it is a manifestation of how mass and energy warp the fabric of space-time. This shift is crucial. Gravity is no longer about things pulling on each other across a distance. It's about objects moving along curves in space-time geometry, curves created by mass energy. That's the key phrase, mass energy. Not just mass. Energy, too, creates gravity. And since light is pure energy, it follows that light, despite being massless, can and does affect the curvature of space-time. This is not a theoretical guess. It's an experimentally verified reality. We have literally seen light bending space-time, and we've seen space-time bending light. Let's start with what we observe. Light is affected by gravity. One of the most famous confirmations of Einstein's predictions came in 1919 during a solar eclipse. As the moon blocked the sun's light, astronomers could observe the positions of stars behind the sun. What they saw was that the stars' positions appeared slightly shifted. The light from them had been bent as it passed near the massive sun. The curvature of spacetime caused by the sun's mass had deflected the path of the photons, altering their apparent position. This phenomenon, now called gravitational lensing, has become one of the most powerful tools in modern astrophysics. We see entire galaxies distorted by the gravitational influence of invisible masses in the foreground, often black holes or dark matter halos. This tells us something profound. Light, though it has no mass, follows the curves and contours of spacetime just like any massive object would. But the reverse is also true, and this is where it gets even more intriguing. Light itself curves spacetime. To understand this, we must go deeper into Einstein's equations, specifically the Einstein field equations, which relate the geometry of spacetime, described by the Einstein tensor, to the energy and momentum content of that region, described by the stress-energy tensor. This stress-energy tensor includes mass energy, momentum, pressure, stress like tension or compression, and most importantly here, electromagnetic energy, which includes light. This means that a sufficiently intense beam of light carries enough energy and momentum to influence spacetime in the same way that matter does. The more energy packed into a photon stream, the more intense its gravitational influence becomes. For everyday levels of light, like the glow of a candle or even a powerful laser, the gravitational effect is so minuscule that it's utterly undetectable. But if you scale up the intensity by many orders of magnitude, the math becomes unavoidable. In extreme cases, the collective energy of photons can warp spacetime enough to cause self-gravitation. This is not a metaphor, it's a literal prediction of general relativity. An example of this is a theoretical construct known as a photon sphere, which is a region where gravity is so strong that photons can orbit a mass in circular paths. This already occurs around black holes, typically at about 1.5 times the Schwarzschild radius. It's not that the black hole is emitting light, it's that incoming photons from elsewhere can be captured in looping trajectories, tracing rings around the hole. This is another indicator that gravity and light are deeply intertwined. But perhaps the most vivid demonstration of light-producing gravity is the idea of the Kugelblitz itself. If enough light is pumped into a small region of space, its cumulative energy can curve spacetime so sharply that it collapses into a black hole. There doesn't need to be a single particle of mass involved. The photons themselves, due to their energy content, collectively warp spacetime into a closed region from which no information can escape. That's gravity created entirely by light. You could picture this by imagining photons racing inward from all directions, like a perfect spherical implosion of light. Each photon is massless and individually unable to bend spacetime in any appreciable way, but together, their energy adds up. Their gravitational influence intensifies as their density increases. Once the energy within a small enough volume exceeds the so-called critical energy density threshold, the space they occupy begins to curve inward faster than the photons can escape. In that moment, an event horizon forms. A Kugelblitz is born. Now one might ask, if light can bend spacetime, does that mean it can pull on objects like mass does? Yes, but again, the effect is infinitesimally small at normal scales. In practice, the gravitational pull of a laser pointer is undetectable. But mathematically it's there. Photons carry momentum and energy, and both are sources of spacetime curvature. In fact, extremely powerful laser pulses can impart tiny amounts of momentum to particles, not just from radiation pressure, but from the very curvature their energy produces. In more advanced theoretical physics, such as in the study of null dust, a model used to describe massless radiation in general relativity, we see how collections of photons traveling in a specific direction can curve spacetime in measurable ways. Even in high-energy particle collisions, tiny, fleeting concentrations of energy in the form of radiation may produce localized warping of space, possibly even forming micro-black holes under extreme conditions. This leads us to another thought-provoking point. In the early universe, just moments after the Big Bang, radiation dominated everything. Temperatures were so high that matter hadn't yet formed, only energy, flying through space at incomprehensible intensities. During this epoch, the gravitational effects of light weren't just noticeable, they were cosmic in scale. It's entirely possible that in those early seconds, regions of concentrated radiation curved spacetime enough to produce primordial black holes, early kugelblitzes, born not from collapsing stars, but from the intensity of creation itself. So yes, light can absolutely have gravity. It may be massless, but it is never powerless. Through its energy, its momentum, and its density, it can bend the universe. It can alter the trajectories of objects. And under the right conditions, it can collapse upon itself to become something utterly paradoxical, a singularity of darkness made entirely from light. This is one of the most surprising, beautiful, and profound truths of modern physics. The most ethereal phenomenon, something that travels without mass, that we associate with clarity, vision, and life, can, if pushed hard enough, become a force of such overwhelming influence that it reshapes spacetime itself. It reveals a deeper unity in the laws of nature. It reminds us that mass and energy are two sides of the same coin. And it offers a new way to think about gravity, not as something tied only to solid, tangible things, but as something that can emerge from the very act of intensity. Light can create its own gravity. And in doing so, it becomes one of the most powerful sculptors of the universe's architecture. Could humanity, in some distant future, build a machine capable of creating a Kugelblitz, a black hole made entirely from concentrated radiation? Could we construct a device so powerful, so precise, that it focuses light into a point so intensely that spacetime collapses under its weightless energy? The idea may sound like pure science fiction, and in many ways it still is. But within the laws of known physics, the concept remains theoretically possible. Let's explore just how such an audacious feat could, in principle, be achieved. To begin, the challenge is one of energy concentration. The problem isn't just producing light. We do that every day. Even generating powerful light is within reach. Lasers can produce pulses of enormous intensity. But creating a kugelblitz doesn't just require intense light. It requires such a massive amount of energy, focused into such a small space, that the energy density reaches levels high enough to bend spacetime into forming a singularity. Let's quantify that. As discussed earlier, to create even the smallest possible black hole, one with the mass of, say, a mountain, you would need on the order of 10 superscript 3 superscript 1 to 10 superscript 3 joules of energy. That's more than all the energy currently available on Earth. In fact, it's vastly more than the energy humanity has consumed in its entire history. To get a sense of scale, the total energy output of the Sun is 3.8 x 10 superscript 2 joules per second, so you need to capture and concentrate the output of the entire Sun for several days, and funnel it into a region no larger than an atomic nucleus. This leads us to the first major hurdle: energy generation and storage. Currently, our energy production methods, from fossil fuels to nuclear power, are embarrassingly small on this scale. Even the most advanced energy storage systems, like superconducting magnets or antimatter containment, are many orders of magnitude below what would be needed to create a kugelblitz. So before anything else, we would need to master the control of energies that dwarf the power of planets. Next, consider energy focusing. Let's suppose, for a moment, that we have the energy. The next step is to focus it, not just into a point, but into a precise, coherent volume, likely on the order of Planck scale dimensions for extremely small black holes. You can't just shine a bunch of flashlights at a rock and expect to get a kugelblitz. You need to direct an immense number of high-frequency photons, likely gamma rays or X-rays, toward a single point in spacetime with zero dispersion, total synchrony, and perfect symmetry. This is where high-energy gamma-ray lasers, or grazers, enter the discussion. Though purely theoretical, grazers would emit coherent gamma radiation with enough intensity to possibly approach the energy thresholds needed. Building one would require exotic materials, quantum-level coherence control, and some type of energy harvesting system that makes today's nuclear reactors look like AA batteries. But how would you even hold the photons in place long enough for them to collapse? Photons travel at light speed. They don't sit still. They don't accumulate in one spot. The moment you release them, they're already on their way out. So any successful kugelblitz generating device would need some kind of perfect focusing shell, a structure, natural or artificial, capable of bending every photon inward at precisely the same time and angle. This structure would need to contain no matter at its core, only vacuum, and be built from something that can withstand unimaginable radiation pressure. One proposed design is a kind of spherical mirror array, perhaps built with gravitational lensing itself. Imagine an enormous Dyson sphere-like structure, not to harvest starlight, but to redirect it. Photons are emitted from the inner walls of the sphere and all converge at the exact center of the sphere. If the energy is high enough, and the convergence is perfect, then theoretically, the radiation at the center could become dense enough to collapse into a black hole. An even more exotic idea would be to use a ring of black holes or neutron stars to create a natural gravitational lens that can fold light inward. This would take planetary engineering on an absurd scale, the kind of project only imaginable by Kardashev Type 2 or 3 civilizations, those capable of manipulating energy on the scale of entire star systems or galaxies. But even if we could generate the energy, focus it, and direct it, there remains the ultimate question: containment. Once formed, a kugelblitz would, by definition, be a black hole, and it would begin pulling in anything nearby. How would you prevent it from immediately consuming the structure that created it? How do you contain a black hole? One theoretical answer is to let it evaporate. If the black hole formed is small enough, say microscopic, then it would rapidly emit Hawking radiation and disappear before it has time to do damage. These short-lived kugelblitzes could be generated in secure vacuum chambers, with their energy emissions harvested before they vanish. Some have even proposed using such kugelblitzes as power generators, where the energy extracted from the rapid evaporation could be converted to usable electricity, albeit with absurdly advanced containment fields. Another idea is to trap it magnetically, not because black holes respond to magnets, but because you could trap the environment around the black hole, creating a sort of artificial gravity cage using space-time curvature itself. This gets into the realm of advanced space-time engineering, a science that doesn't yet exist, but which isn't outright forbidden by physics. And if you want to go even further, some science fiction authors and futurists have envisioned Kugelblitz engines, propulsion systems that use miniature black holes to push starships across galaxies. The idea is to create a small black hole, feed it matter to keep it stable, and then use its Hawking radiation as a directed thrust. To do this with a Kugelblitz, you'd create a black hole from light itself, keep it caged, and steer it across the stars. It's the ultimate in theoretical technology, turning concentrated brightness into the darkness that propels humanity to other worlds. But let's step back for a moment. Could we really do any of this? With today's technology, no. We're not remotely close. The energy levels, engineering precision, and understanding of gravitational control required are beyond anything our civilization can manage. It's like asking an ant to build a space station. We're still in the early candle-burning stages of energy mastery. Our greatest lasers, like those at the National Ignition Facility or the European XFL, are brilliant, but they are toys compared to what would be needed to attempt a Kugelblitz. Yet the principles themselves aren't forbidden by physics. That's what makes the concept so tantalizing. If a civilization had sufficient energy resources, advanced materials, and an understanding of quantum gravity, it could, in principle, build a Kugelblitz generator. It might be used as a power source, a weapon, a propulsion system, or simply as a cosmic experiment. And what would happen the first time they succeeded? A burst of light focused with unimaginable force, then total silence. A black dot hanging in midair, a hole in space itself, created not from mass, not from matter, but from pure radiant will. A star that never was. A singularity birthed from brilliance. It would mark not just a technological achievement, but a philosophical one. For the first time, intelligent life would have reached into the structure of space-time itself and torn it open with nothing more than the concentrated light of its own making. Not destruction. Not death. But transformation. The birth of gravity from light. To understand how light, or more precisely, photons, can lead to the formation of something as extreme as a black hole, we need to dive into the strange, elegant realm of quantum field theory. This is where classical ideas of particles and waves dissolve into a richer, more fundamental framework, one in which everything, from electrons to photons to spacetime itself, emerges from fields vibrating with energy. At the heart of this framework is the idea that every particle we observe is actually an excitation of an underlying field. The universe isn't a collection of things moving around in empty space. Instead, it's a sea of overlapping, omnipresent fields, one for every fundamental force and particle. The photon, the fundamental particle of light, is the quantum excitation of the electromagnetic field. You can think of the electromagnetic field as an invisible ocean that fills all of space. A photon is like a ripple, or wave, traveling through that ocean, but unlike ripples in water, photons are quantized. They come in discrete packets of energy, with no in-between. They don't slow down, they don't rest, and they always move at the speed of light in a vacuum. Now here's where things get interesting. While a single photon is practically harmless, carrying only a tiny amount of energy, an enormous number of them, oscillating in coherence, can generate a collective wave so intense that it alters the very structure of reality. This brings us to the idea of energy concentration in quantum fields, and why focusing a huge number of photons in one region of space can distort spacetime. In the quantum world, energy is not just a property of particles. It's a manifestation of how active the field is at a certain point. If you inject energy into the electromagnetic field, for example, by firing a high-powered laser, you're creating a coordinated surge in photon activity. The field becomes excited, and the density of those photon quanta in that region of space increases. Photons are bosons, which means they can occupy the same quantum state. That's unlike fermions, which obey the Pauli exclusion principle. No two fermions can occupy the same state at the same time. Because photons are bosons, they can stack. You can concentrate millions, billions, or trillions of them in a single coherent wave, as happens in a laser beam. This bosonic stacking is essential for any attempt to reach the kind of energy density necessary to warp spacetime. In effect, you're pouring more and more photons into a tiny region of the electromagnetic field, amplifying its energy density with no theoretical upper limit, until it reaches the point where general relativity says, this field is now heavy enough to collapse spacetime. This brings us to the stress-energy tensor in general relativity, the mathematical object that describes how matter and energy affect spacetime curvature. It doesn't care whether the energy comes from matter, radiation, or vacuum fluctuations. If the tensor says the energy density is high enough in a small enough volume, then spacetime must curve. Curve it enough, and a gravitational singularity forms. In a highly focused laser pulse, or a spherical convergence of gamma photons, the local energy density of the electromagnetic field becomes the central actor. Every added photon strengthens the gravitational imprint of that field. Even though each individual photon has no rest mass, their collective energy and momentum are sources of gravity. From a quantum field theory perspective, creating a Kugelblitz would mean manipulating the electromagnetic field so forcefully, so precisely, that its excitations coalesce into a gravitationally self-trapping wave. You wouldn't need any physical object to push or pull, just an overwhelming surge of field energy folding into itself. But photons also have a unique feature in the quantum world. They always move at light speed, and they have no rest frame. You can't stop a photon to measure its location in the same way you can stop an electron. This adds to the challenge of forming a Kugelblitz. You're trying to collapse a field made of particles that never stop moving, and that inherently want to spread out. That's what makes the idea so paradoxical, and so fascinating. You're attempting to use motion to create confinement, using speed to induce gravitational stillness. Let's take this a step deeper into the quantum. The electromagnetic field isn't just a sea of ripples, it's also the foundation for virtual particles, short-lived particle-antiparticle pairs that flicker in and out of existence in empty space. These fluctuations are normally harmless and barely measurable. But in extreme energy environments, such as those created by ultra-intense lasers or in the early universe, virtual photons can contribute to the energy density of the vacuum. This concept hints at how vacuum polarization and quantum electrodynamics, QED, might play a role in high-energy field collapses. If the vacuum itself can become energetically active, it might enhance the formation of singularities through subtle feedback loops between the field and spacetime. In essence, the more energy you inject into the field, the more the vacuum fights back, and if it loses, you get a black hole. Even more tantalizing is the idea of coherent states of light, like those found in laser beams. In these states, photons aren't just concentrated, they're organized. They move in phase, with precise alignment. This coherence may be critical to avoiding destructive interference and maximizing energy density in a small volume. A truly ideal Kugelblitz generating system would need to exploit this coherence on an astronomical scale, trillions of gamma photons pulsing inward with quantum-level precision, guided by technology we have yet to invent. But what makes this topic so endlessly captivating is that it bridges two of the greatest theories in science: quantum field theory and general relativity. Photons are creatures of the quantum world, probabilistic, delocalized, wave-like. But the gravity they can create is classical and geometric, smooth, continuous, and deterministic. A Kugelblitz sits right at the intersection of these regimes, challenging us to unify our understanding of the smallest and largest structures in the universe. Could studying these photon-induced gravitational collapses help us find the long-sought theory of quantum gravity? Maybe. Because the Kugelblitz is a perfect case study, a singularity created not from matter, but from pure field excitation. If we ever find a way to describe what happens to the quantum state of those photons as they cross the event horizon, we might unlock the secrets of black hole information, Hawking radiation, and spacetime itself. And let's not forget the poetic element here. The very thing that gives us sight, light, becomes, at the limits of concentration, blind. It forms a prison it cannot escape. Not through absorption, not through reflection, but through gravitational surrender. So, in the language of quantum fields, a Kugelblitz is light that's too intense to remain light. It's photons stacking in phase until the field itself becomes curved, until the vacuum breaks, and until space-time concedes to brightness by forming darkness. From the vibration of a field, to the silence of a singularity. So, if you could somehow forge a Kugelblitz, focus pure light so intensely that it collapses into a black hole, would it be any different from the ones formed from stars? Would a black hole made of photons behave differently than one made of atoms? Surprisingly, the answer from Einstein's general relativity is no, at least from the outside. A black hole is a black hole, regardless of what formed it. This idea is beautifully encapsulated in a principle known as the no-hair theorem. It tells us that black holes, no matter how they were born, can be fully described by just 3 parameters. 1. Mass. 2. Electric charge. 3. Angular momentum, spin. That's it. Everything else, the details of how the black hole formed, what kind of material or energy went into it, whether it was matter or radiation, is erased from the observable universe. Once the event horizon forms, all that internal history gets lost behind it, inaccessible to any external observer. So if you had a stellar black hole and a Kugelblitz black hole with the same mass, charge, and spin, and placed them side by side in space, you couldn't tell them apart. They would bend space-time identically. They would curve light paths identically. They would cause identical time dilation and identical tidal effects on surrounding matter. Even Hawking radiation, the faint quantum leakage predicted to slowly evaporate black holes, would be the same for both, assuming equal mass. This is one of the strangest and most unsettling truths of black hole physics. Once a black hole forms, its origin is deleted from reality. A singularity has no memory. But that doesn't mean all black holes behave identically at every stage of their lives. Let's look deeper, especially at formation, surroundings, and evolution, to explore where subtle differences might emerge. First, consider the formation process. A stellar black hole is born from a gravitational collapse. Its process is violent, messy, and explosive. A massive star, reaching the end of its nuclear fuel, implodes under its own gravity. The core collapses to a singularity while the outer layers may blast away in a supernova. This process leaves behind traces, heavy elements, high-energy particles, shockwaves, possibly a neutron star or white dwarf nearby. We can often observe these birth pangs indirectly, through X-rays, gamma-ray bursts, gravitational waves, or expanding gas clouds. A Kugelblitz, in contrast, might form quietly. If it forms in deep space from converging beams of radiation or in an artificial chamber, it may produce no such explosive traces. It might suddenly appear, a new gravitational source, dark and silent, in a region where no massive star ever existed. That subtlety makes it much harder to detect. Additionally, a Kugelblitz might be smaller. Because it's not constrained by the size of a collapsing star, it can be created, in theory, at any mass, as long as the energy threshold is met. That means it could be microscopic, formed by a burst of extremely concentrated gamma rays. Such a mini Kugelblitz would be highly unstable and evaporate quickly through Hawking radiation, perhaps in fractions of a second. Stellar black holes, on the other hand, are huge and long-lived. Their Hawking radiation is so weak that it would take more than the current age of the universe for them to vanish. In fact, Hawking radiation provides one of the few theoretical ways to tell the difference, indirectly. Since smaller black holes radiate more strongly, a tiny Kugelblitz would emit a more intense, shorter-lived burst of particles as it evaporates. If we ever detected such a burst in a controlled experiment, or from space, it might hint at a black hole formed from concentrated energy rather than matter. Another area where differences might arise is charge. Photons are neutral, but in some theoretical constructions, beams of radiation could carry a net electromagnetic effect, for example, through polarization or interactions with surrounding charged particles. A kugelblitz formed in this way might have an unusual charge profile at formation. However, such charge would still fall under the charge component of the no-hair theorem, meaning it wouldn't violate external symmetry. What about spin? Black holes can rotate. In fact, many observed astrophysical black holes spin rapidly, inherited from the angular momentum of the stars that formed them. A stellar black hole's spin is a natural result of its progenitor's rotation. A kugelblitz, however, might be designed or focused to be perfectly symmetric, meaning no net angular momentum. Or it might be generated from rotating beams of light, giving it a custom-designed spin. So in that sense, kugelblitzes might offer more tunability. An artificial one, for example, could be engineered to have minimal spin or be maximally rotating, something difficult to control in stellar black holes. A spinning black hole behaves differently from a non-rotating one, particularly in terms of frame dragging and ergospheres. So in a lab or advanced civilization scenario, a kugelblitz could serve as a tailored, gravitational object. Then there's the question of what's inside. This remains one of the most mysterious areas of black hole research. According to classical general relativity, the singularity is a point of infinite density. But we know this can't be the whole story. Quantum mechanics must modify this picture at incredibly small scales. Some physicists speculate that the internal structure of a black hole might retain information about its formation at the quantum level, possibly encoded on the event horizon itself via the holographic principle. If that's true, then maybe, just maybe, a kugelblitz has some unique internal quantum fingerprint, even if it's completely invisible from the outside. This leads into the black hole information paradox, the puzzle of whether information about the material that formed a black hole is truly lost forever or subtly encoded in Hawking radiation. If a kugelblitz is created from coherent photons, a very specific quantum state, then the information question becomes even more urgent. Does the black hole destroy that coherence? Or could the Hawking radiation somehow reflect it back, bit by bit? In that sense, kugelblitzes might become an ideal testing ground for theories of quantum gravity. They're clean, radiation-only black holes. If we can eventually study their formation, evaporation, and interactions, we might uncover new insights about the quantum fabric of spacetime, insights hidden by the messy birth of stellar black holes. Finally, there's a profound philosophical angle. A black hole formed from matter suggests collapse, a failure to resist gravity. But a black hole formed from light suggests overflow. Too much energy. Too much radiance. It's the idea that even brightness can become a burden. That photons, when too numerous, too intense, fold in on themselves and vanish. From the outside, a kugelblitz may behave just like any other black hole. But the story behind it, the physics, the energy, the silence after the light, makes it something fundamentally different. A black hole not born from the ashes of a dying star, but from the concentration of creation itself. It's not the collapse of mass into silence. It's the collapse of brilliance into shadow. Could nature itself have beaten us to the punch? Could kugelblitzes, black holes made purely of light, have already formed somewhere in the vast timeline of the cosmos, not in laboratories, but in the wild cauldrons of astrophysical violence? While we've never directly observed one, the laws of physics don't forbid their natural creation. In fact, under the right conditions, the universe may have already spawned kugelblitzes, quietly, subtly, and long before the first stars were born. Let's begin our speculation where everything began, the early universe. In the first few microseconds after the Big Bang, the universe was a dense, seething ocean of pure energy. Temperatures soared above 10 superscript 3 superscript 2 Kelvin. At this level of intensity, matter as we know it didn't yet exist. There were no atoms. No protons or neutrons. Just raw energy, photons, gluons, gravitons, and other quantum fields bubbling violently in an almost featureless soup. During this radiation-dominated era, the energy density was staggeringly high, and most of it existed in the form of light and other massless or nearly massless particles. Now, imagine this energy wasn't distributed perfectly evenly. Inflation, The rapid exponential expansion of the universe is thought to have smoothed things out, but tiny quantum fluctuations would have remained. These fluctuations in energy density would later give rise to the large-scale structure of the universe: galaxies, clusters, voids. But in these very earliest moments, if a particular fluctuation spiked beyond a critical threshold, it might have been enough to cause a local collapse of spacetime. And here's where it gets interesting. In those first moments, matter didn't exist yet, or it was still forming. So any such collapse would have to occur due to radiation, not mass. This sets the stage perfectly for the natural formation of primordial kugelblitzes. These would be the earliest black holes in existence, not formed by stars, but by pockets of radiation dense enough to trigger gravitational collapse. If such objects did form, they may have been tiny, perhaps with masses no greater than that of a mountain or an asteroid. These miniature black holes would have had incredibly short lifespans, vanishing through Hawking radiation in fractions of a second. But for the brief time they existed, they would have been gravitational monsters, ripping through the early plasma, distorting time and space, perhaps even spawning gravitational waves. In fact, there are theoretical models in cosmology that predict the formation of primordial black holes, PBHs, black holes formed during the first second after the Big Bang. Some researchers speculate that PBHs could even account for part of the dark matter in the universe. While most PBH models assume mass-driven collapse, the idea that some of them could have been kugelblitzes, born from pure radiation spikes, is completely consistent with the physics. And that's not the only place they might form. Let's fast forward to a more mature universe. A place filled with galaxies, stars, and jets of incomprehensible energy. Even today, there are cosmic events so powerful that the radiation they release makes our best lasers look like flickering candles. Consider gamma-ray bursts, GRBs. These are the most energetic explosions known in the universe. Some GRBs release more energy in a few seconds than the Sun will emit in its entire lifetime. The source of these bursts is still being investigated. They might come from merging neutron stars, collapsing supermassive stars, or other exotic phenomena. But what's consistent is this: they involve the sudden release of intense, focused radiation, concentrated into narrow jets that blaze across the cosmos at nearly the speed of light. Now imagine if two such jets intersected, or if some unusual gravitational configuration caused that energy to reflect and focus upon a point. Could the photon density reach a critical threshold? Could the sheer intensity of gamma photons in a confined region collapse spacetime into a kugelblitz? It's unlikely under typical circumstances, but in the chaos of extreme astrophysics, unlikely doesn't mean impossible. The energy densities required are enormous, but nature often works on scales far beyond our machines. Another candidate location? The hearts of active galactic nuclei and quasars. These regions already host supermassive black holes, but they also produce relativistic jets that span thousands of light years. These jets are composed of highly collimated, ultra-energetic particles and photons. In rare cases, their geometry might create localized photon densities beyond the critical limit, particularly if magnetic fields or gravitational lensing folds the radiation back upon itself. Such a scenario could, in theory, generate a localized kugelblitz, a gravitational singularity born not of collapsing matter, but from feedback loops of light. And let's not ignore the universe's most ancient and mysterious background signal, the cosmic microwave background, CMB. The CMB is the afterglow of the Big Bang, the fossil radiation of a once raging fireball. It is incredibly uniform, but small anisotropies exist, tiny hot and cold spots. Some fringe theories suggest that certain regions of the CMB may preserve the gravitational signatures of early black hole formation. If any of those were formed by radiation collapse, they could be ancient footprints of primordial kugelblitzes. There's also the tantalizing possibility that we've already seen something like a kugelblitz, and simply didn't know it. Maybe a sudden, unexplained burst of gravitational waves, not associated with any detectable merger, could hint at the birth of a radiation-born black hole. Or maybe a faint, short-lived gamma signal, quickly fading to nothing, was the death cry of a microscopic kugelblitz evaporating into the vacuum. These signals would be rare, brief, and easily missed. But future generations of detectors, more sensitive and more comprehensive, may one day pick them out of the cosmic noise. So, are there kugelblitzes in nature? No direct evidence, yet. But the cosmos is vast, violent, and extraordinarily creative. It has had 13.8 billion years and more energy than we can comprehend to work with. And the physics is clear: if the energy density is high enough, regardless of whether it comes from mass or light, spacetime must yield. It must bend. It must collapse. It's hard to imagine that, in all that time, under all that pressure, the universe never once focused light into darkness. Somewhere out there, perhaps in the unobserved past or in a far-off corner of the cosmos, a flash of brilliance may have burned so hot and so sharp that it turned inward. It folded space. It swallowed itself. And in a place where nothing material collapsed, only radiation, a kugelblitz may have been born, silent, perfect, and blind. If a kugelblitz, a black hole made entirely from pure light, were to form, would it fade away like any other black hole, dissolving slowly through Hawking radiation? And if so, how fast would this light-born singularity vanish? To answer this, we need to step into the strange intersection of quantum mechanics and general relativity, where the classical notion of a black hole, a region from which nothing can escape, becomes blurry, uncertain, and slowly leaky. This is where Hawking radiation enters the story, and it changes everything. Stephen Hawking's groundbreaking insight in 1974 revealed that black holes aren't completely black. Instead, quantum fluctuations at the event horizon, the boundary where escape becomes impossible, cause pairs of virtual particles to pop into existence. Normally, these particles annihilate instantly. But near a black hole's event horizon, one of the particles can fall in while the other escapes into space. From the outside, it looks like the black hole is slowly radiating energy. This effect is universal. It doesn't care what the black hole was made of. Whether the singularity originated from collapsing atoms, a dead star, or pure radiation, like a kugelblitz, the resulting black hole should emit Hawking radiation in exactly the same way. That's because Hawking radiation depends entirely on the mass, charge, and spin of the black hole, not its origin. Once the event horizon forms, everything inside becomes causally disconnected from the outside world. The quantum vacuum near the horizon behaves the same, no matter what lies within. And so, yes, a black hole formed from photons will evaporate. But how fast? The rate of Hawking radiation is inversely proportional to the mass of the black hole. In simple terms, the smaller the black hole, the faster it evaporates. A stellar mass black hole, say one with a mass similar to our Sun, loses an unimaginably tiny amount of energy through Hawking radiation, something like watts. It's negligible. It would take longer than the current age of the universe, many trillions of years, for such a black hole to evaporate completely. But a kugelblitz is likely to be much smaller than a typical stellar black hole. Why? Because producing a black hole from radiation requires such an extreme concentration of energy that it's far more feasible, though still outrageously difficult, to create a small one. A microscopic kugelblitz, for example, with the mass of Mount Everest, about kilograms, would evaporate much faster, potentially in a matter of billions of years. Still long by human standards, but far shorter than its stellar cousins. And it gets faster. If you made a kugelblitz with the mass of a large asteroid, say kg, it could evaporate in millions of years. Drop it down to the mass of a mountain, kg, and it might vanish in a few thousand years. A kugelblitz with the mass of a small car, around kg, could evaporate in fractions of a second, radiating away its entire mass in a sudden, blistering flash. In the final moments of evaporation, the process accelerates rapidly. As the black hole loses mass, its surface gravity increases, which boosts the energy of the emitted Hawking radiation. The temperature of the black hole rises as it gets smaller, inversely proportional to its mass. In the final milliseconds of its life, a kugelblitz might emit a burst of high-energy particles and radiation, like a subatomic supernova. If we ever create or observe such an event, the last few moments could be incredibly violent. A surge of gamma rays, neutrinos, and particle-antiparticle pairs erupting into space. This has led some physicists to propose that evaporating micro-kugelblitzes might be detectable in the cosmos, through short bursts of gamma radiation, or by their gravitational influence before they vanish. However, such events would be rare, extremely brief, and hard to distinguish from other high-energy cosmic phenomena. But this rapid evaporation raises another deep question: what happens to the information? If a kugelblitz was made from coherent photons, a highly ordered, quantum state of light, then what becomes of that order? Does Hawking radiation emit random thermal noise, or does it somehow encode information about the original light configuration? This is the heart of the black hole information paradox, and it's no less mysterious for light-borne black holes. Some researchers believe that the answer may lie in the quantum structure of spacetime itself, or in the concept of black hole complementarity, the idea that different observers might see different versions of reality near a black hole, and no contradiction arises because they can't compare notes. Others lean on the holographic principle, which suggests all information falling into a black hole is stored at the event horizon, like a two-dimensional projection of a three-dimensional system. If true, this could mean that even a kugelblitz, born from focused beams of gamma light, has its structure preserved, holographically, until its last evaporative breath. And what would that look like? The final gasp of a small kugelblitz might resemble a blinding, silent explosion. Not the roar of thunder, not the fireball of combustion, but a flood of high-frequency radiation, popping into being from the quantum void. To us, it might look like a sudden gamma-ray flash from nowhere, leaving behind no ashes, no debris. Just energy, liberated from a prison of infinite density. And here's a poetic irony to ponder. A kugelblitz is made from light. It collapses into a region where no light can escape. But in the end, through Hawking radiation, it returns to light once again. Its birth is brightness. Its death is brightness. In between lies the silence of a black hole, a stillness that bends time and space. But from start to finish, it is a journey of photons. A cycle of light becoming gravity, then gravity becoming light. If ever a black hole held a secret signature of its own radiance, it would be the kugelblitz. As you approach the edge of a black hole, any black hole, even one formed from pure light like a kugelblitz, the flow of time does something almost magical. It bends. It slows. It stretches toward a halt. To an outside observer watching you from a safe distance, your every motion begins to look strange. If you waved, your hand would appear to move slowly. If you blinked, the flutter of your eyelid would seem to take minutes. As you approach closer and closer to the event horizon, that invisible boundary beyond which nothing, not even light, can return, you would seem to freeze in place, hanging there for all eternity. But to you, the traveler falling inward, time feels perfectly normal. This is the wonder of gravitational time dilation. Time flows differently depending on how deep you are within a gravitational field. Near a massive object, time ticks more slowly relative to regions of weaker gravity. And a black hole, even a small one like a kugelblitz, generates the most intense gravitational field known. It doesn't matter whether that black hole was born from a dying star or forged from an impossibly dense sphere of radiation. Once the event horizon forms, the gravitational rules are the same. Mass, light, energy, they all bend spacetime, and spacetime controls time itself. So imagine a scenario. A tiny kugelblitz the size of a marble floats in space. You carefully position yourself in a stable orbit just a few meters above its event horizon. From your perspective, you're calmly orbiting. Maybe you're looking down at it, or transmitting data back to a ship hovering farther away. Your heartbeat feels steady. A minute passes for you. Maybe two. But back on that distant ship, or on Earth, weeks, months, or even years might pass in the same span. To your friends, your voice has become delayed. Your signals grow slower and slower. The light reflecting off your spacecraft takes longer to reach them, redshifting into deeper and deeper wavelengths. If you dared to hover even closer, that time stretch would grow more extreme. A few seconds for you might equal a lifetime to someone else. Your story would be playing out in slow motion across the universe. If someone were filming your descent from afar, they'd never see you cross the horizon. You would appear forever frozen at the edge, a silhouette caught at the boundary between light and shadow. This isn't just poetic, it's real physics, confirmed by everything from GPS satellites to clock experiments on mountaintops. Clocks tick slower in stronger gravity. The closer you are to a gravitational source, the slower your time moves relative to someone farther away. In the case of a kugelblitz, time dilation could be even more dramatic than with a typical stellar black hole. Why? Because kugelblitzes are often theorized to be much smaller, possibly formed by compressing vast amounts of radiation into a volume no larger than a baseball, a marble, or even a subatomic point. Smaller black holes have steeper gravity wells near their surface. That means you don't need to be very far from the center to feel a radical shift in time's flow. In fact, if you got too close, you'd experience what's known as spaghettification, where the difference in gravitational pull between your head and feet becomes so extreme that you're stretched like a noodle. But long before that terrifying effect takes hold, time itself will have already betrayed you. Your thoughts, your actions, your breath, all will be unfolding in a slowed reality, disconnected from the rhythm of the rest of the universe. And what happens once you cross the event horizon? From your point of view, you pass through seamlessly. Time continues normally for you, until you reach the singularity, the point at the very center where space-time becomes infinitely curved. There, according to general relativity, your future ends. But no message, no light, no data from your journey can escape back across the horizon to tell the outside universe what you saw. To everyone else, you never actually cross. You hover there, slowed to an eternal crawl, redshifted into blackness. So in the case of a kugelblitz, the paradox is especially poetic. It's a black hole made from light, the very thing that defines speed, energy, and visibility. Yet as you approach it, light itself becomes prisoner to time. And time becomes a labyrinth. The light that created the black hole now forms a trap from which no new light, or time, can escape. You could fall into a kugelblitz and experience a smooth flow of minutes or hours. But the rest of the universe would grow ancient in your absence. Stars would die. Galaxies would drift. Civilizations would rise and fall. All while, from their perspective, you remained at the edge of light. It's not just that space is curved near a kugelblitz, time is too. And when time curves, we begin to lose our grip on everything we once thought steady: rhythm, change, motion, age. You could say a kugelblitz doesn't just capture light. It captures time itself. It becomes a bubble where clocks run to a different beat, a slower beat, and reality outside moves faster and faster until it's out of reach. To approach a kugelblitz is to walk into the future, while leaving your own behind. Could you see a kugelblitz coming? Would it glow like a star? Flash like lightning? Would its approach cast eerie shadows or shimmer with radiation? The truth is far stranger, and far darker. Despite being made entirely from light, a kugelblitz becomes the very thing that devours all light. The moment its energy crosses the critical threshold and collapses into a gravitational singularity, something remarkable and paradoxical happens. The light that created it vanishes, not by fading, but by falling in on itself. The result is a black hole. A perfect absence. A region of space from which nothing, not even light, can escape. So from the outside, a kugelblitz would be invisible. You wouldn't see a sphere of glowing radiation flying through the cosmos. You wouldn't see a bright orb of focused photons rushing towards you like a celestial weapon. Once formed, the kugelblitz would behave just like any other black hole, an object with no surface, no texture, no features. Just a sphere of complete darkness floating against the backdrop of stars. But it wouldn't go completely unnoticed. Because even though the kugelblitz emits no light of its own once it's formed, it bends the light of everything around it. The intense curvature of spacetime near the event horizon acts as a gravitational lens, distorting the light of stars, galaxies, and cosmic dust behind it. From a distance, this effect might be the only clue to its presence. You might spot a warped halo, a circular ring, or a shifting smear of background light where spacetime is being twisted. This effect is called an Einstein ring, and it has been observed around massive black holes before. Imagine looking at the sky and seeing a faint circle where no star should be. No light comes from within the circle itself, but all around it, starlight bends strangely, curving inward as if skirting the edge of something hungry and hidden. That circle might be the only sign that a kugelblitz is there. But the key word here is might, because depending on the size of the kugelblitz, even this gravitational lensing could be incredibly subtle. A microscopic kugelblitz, for example, one with the mass of a mountain, would be far too small to visibly distort starlight to the naked eye or even a telescope. It could drift silently through the solar system, and we never see it unless it interacted with something nearby. Larger kugelblitzes might be easier to detect by their gravitational influence. If one passed close to a planet or a spacecraft, it would subtly tug on it, changing its orbit, causing anomalies in trajectories, or distorting radio signals sent nearby. In this way, we might infer the presence of a kugelblitz not by what it emits, but by what it disrupts. And then there's the matter of accretion. If the kugelblitz encounters matter, gas, dust, or stray particles drifting through space, it could begin to feed. As that material spirals in, it heats up due to friction and compression, forming a glowing accretion disk. This hot, bright disk would shine across many wavelengths, from visible light to X-rays. The black hole itself would remain dark, but the region around it could become luminous. So, in some cases, a kugelblitz might masquerade as a quasar or an X-ray binary, depending on what it's eating. But that requires matter to be present. In deep interstellar or intergalactic space, a kugelblitz might roam without encountering much of anything, leaving no accretion disk, no jet, no glow. Just a moving distortion in gravity, quietly reshaping the path of light and objects that come too close. And what about motion? Would you see a kugelblitz approaching? It depends on how fast it's moving and how close it is. A stationary or slow-moving kugelblitz might sit in place for eons. But if it were somehow flung through space at relativistic speeds, perhaps from a violent birth or a gravitational slingshot, it would become much more dangerous. However, spotting a fast-moving black hole is one of the hardest tasks in astronomy. If it's not feeding on matter or warping the light of stars, it remains nearly invisible. No glow. No reflection. Just a silent bullet of warped spacetime, streaking through the dark. The only warning would come if it passed through or near a dense stellar field. Then, background stars might briefly flicker or distort as the kugelblitz passed in front of them. This effect, called gravitational microlensing, has actually been used to discover unseen black holes. A sudden brightening of a distant star, lasting days or weeks, could indicate that something massive and invisible, perhaps a black hole, is passing in front of it. Still, this method is slow and statistical. It doesn't tell us about individual kugelblitzes in real time. It's more like detecting footprints after the walker is gone. So ultimately, could you see one coming? Not in the traditional sense. You wouldn't see a beam of light or a swirling storm. You wouldn't hear it. You wouldn't feel heat. You wouldn't receive a warning. If the kugelblitz was small, you'd have no idea it was nearby until it either passed through your spacecraft or passed through you. If it was larger, you might detect gravitational anomalies. Light might bend oddly. Radio waves might distort. Stars might shift. But even then, by the time you noticed, it might already be too late to react. In this way, kugelblitzes represent the ultimate paradox. Born of light, yet shrouded in darkness. Forged from photons, yet invisible to the eye. A creature of brightness that hides in perfect black. Their very nature mocks our senses. We see the stars because of the light they send us. We navigate the universe by photons, by reflections, emissions, and scattering. But the kugelblitz erases its own origin. It becomes the absence. It turns light into a prison, and then hides in the silence. Could we see one coming? Only if it wanted us to. But it never will. Imagine a civilization so advanced it could sculpt stars, bend gravity like clay, and command the raw fabric of spacetime itself. A civilization with technology so refined, physics so deeply understood, that it could pull energy not just from suns, but from the very structure of the universe. For them, building a kugelblitz, a black hole born not of matter, but of concentrated light, wouldn't be a theoretical fantasy. It would be a deliberate, engineered act. To create a black hole from light, you need only one thing: energy. A staggering, almost inconceivable amount of it, compressed and directed into a region of space so small that the energy density becomes catastrophic. Gravity doesn't care whether that energy comes from a collapsing star or from a wall of gamma rays. Once the threshold is crossed, space-time buckles. An event horizon forms. And a black hole, a kugelblitz, is born. But how would such a feat be achieved? First, you need a power source. Not just any power source, something orders of magnitude beyond what any human-built device has ever generated. To put it in perspective, to create a kugelblitz with the mass of a small asteroid, you need to compress the total energy output of an entire star, perhaps for days, into a single point. The total solar output of the Sun is around 3.8 x 10 superscript 2 watts. That's 380 trillion watts every second. An advanced species, let's call them a Type 2 civilization on the Kardashev scale, would need access to at least that much energy, and the ability to store and manipulate it with surgical precision. The first step in building a kugelblitz generator would be constructing a Dyson sphere or Dyson swarm, a massive structure that surrounds a star and captures nearly all of its energy. Not just the light, but every bit of radiation and kinetic flux. This energy would then be stored, possibly in superdense exotic matter batteries or converted into ultra-high-frequency electromagnetic waves for efficient transport. Next comes compression. Light naturally spreads out. It doesn't like being focused or confined. Photons repel each other when densely packed, not electrically, but due to quantum field behavior. So to compress light into a black hole, you need to focus it into a region of unimaginably tiny volume. This would require perfect mirrors, materials that don't exist in our current periodic table. Perhaps engineered from programmable metamaterials or structures woven from space-time itself. These mirrors would not just reflect but control the phase, amplitude, and direction of light down to the quantum level. The design might resemble a gigantic spherical chamber, perhaps hundreds or thousands of kilometers wide, in the void of interstellar space, far from planets or stars. Inside, an array of lasers, maybe billions, would fire perfectly synchronized, ultra-high-energy beams inward from every direction. These wouldn't be ordinary lasers. They would fire at frequencies bordering the Planck scale, unimaginably short wavelengths, unimaginably high energies. Beams might not even be electromagnetic in the traditional sense, but something even more exotic: coherent streams of gravitational waves, or high-dimensional energy pulses pulled from the fabric of the vacuum. To ensure every photon arrives at the exact same moment, engineers would need to master quantum timing, synchronizing signals to within fractions of an attosecond. Any deviation, any asymmetry, and the system would fail, the light would scatter, or partially reflect. Only perfect symmetry leads to perfect collapse. As the photons converge, they begin to push space-time inward. They don't touch, photons don't collide like billiard balls, but their energy warps the geometry of space around them. As more and more energy is crammed into this shrinking volume, the curvature intensifies. Soon, a threshold is reached, the Schwarzschild limit. At that precise moment, the energy density becomes so great that a closed surface forms, the event horizon. From that point forward, even the photons that created the kugelblitz can no longer escape. They are now part of the singularity. At the instant of formation, there would be a tremendous release, not of light, but of gravitational waves. The sudden change in space-time topology, from normal space to black hole, would send ripples through the cosmos. A sort of gravitational ping, announcing the birth of something new, a black hole that never touched matter. What would this engineered kugelblitz be used for? To the civilization that built it, the possibilities would be endless. It could serve as an energy sink, a propulsion system, or a data annihilation point. Its immense gravity could be harnessed to bend light, warp time, or power faster than light travel mechanisms, like Alcubierre drives or wormholes. It might even be used in computational experiments, forming the core of a quantum gravity processor that performs calculations with spacetime itself. To contain it, they might construct a gravitational cage, an array of artificial masses, gravitational manipulators, or negative energy fields designed to suspend the black hole in perfect equilibrium. Or perhaps they'd store it inside a vacuum-sealed stasis bubble, isolating it from all matter and preventing growth or decay. The structure would float in interstellar space, monitored by autonomous satellites with AI intelligence beyond imagination, guardians of a light-born singularity. But such technology wouldn't be without risk. If containment failed, the Kugelblitz could drift, feed, and grow. Even a small one, if allowed to interact with matter, could begin swallowing mass and spiraling out of control. A runaway Kugelblitz could become a doomsday engine, erasing planets, collapsing moons, distorting nearby orbits. That's why any civilization advanced enough to create one would also have developed failsafes, quantum kill switches, containment ruptures, or controlled evaporative discharge systems to dismantle the black hole if it exceeded safe thresholds. And yet they might not fear it at all. To them, a Kugelblitz might be no more dangerous than electricity is to us. Tamed. Understood. Routine. From a distance, such a generator would be invisible, its outer shell cloaked against radiation, the singularity inside held in perfect isolation. A hidden starless forge where light is not emitted, but trapped. Silently pulsing with gravitational might. And we, from our primitive place in the cosmos, might only see a flicker. A faint lensing of starlight. A shadow that moves against the sky. A whisper of an intellect so advanced, it builds black holes like we build machines. This is no longer fantasy. It is the logical endpoint of a civilization that has turned knowledge into power, and light into the void. The idea of using a black hole as a battery, as a fuel tank, a generator, even a propulsion engine, sounds like pure science fiction. But when that black hole is a Kugelblitz, forged not from matter but from pure energy, the concept becomes both more poetic and more practical. Because a Kugelblitz is energy, collapsed. It's the ultimate concentration of light, stored in a gravitational prison. And if you could harness that prison, control it, manipulate it, you'd hold the most powerful energy source in the universe. To understand the appeal of a Kugelblitz as a power source, consider the limitations of current, and even speculative energy systems. Chemical fuels like gasoline and hydrogen are woefully inefficient. Nuclear power is better, but still limited. Even fusion, with its promise of clean, nearly limitless energy, barely scratches the surface of what's possible. But black holes, specifically small ones, offer something different entirely. They don't just store energy. They generate it as they evaporate. This is where Hawking radiation re-enters the story. As we explored earlier, black holes slowly radiate away their mass in the form of thermal energy, due to quantum fluctuations at the event horizon. The smaller the black hole, the faster and hotter this radiation becomes. A tiny Kugelblitz, perhaps one with the mass of a mountain or even less, could emit terawatts of energy continuously, in the form of high-frequency particles and radiation. It's a power plant that doesn't need fuel. It just needs containment and time. Imagine a spacecraft powered by a tiny Kugelblitz, held in a magnetic or gravitational containment system, a miniaturized artificial black hole no larger than a grain of sand, glowing invisibly at the core of the vessel. Radiation from its surface is collected and converted into usable power via energy harvesters, perhaps using materials capable of withstanding extreme heat and flux. Every second, this black hole releases energy far greater than any reactor we could build. No fuel needs to be refueled. No waste is produced, except, eventually, more radiation. It's a perfect battery, if you can tame it. This concept was famously proposed in science fiction by physicist Robert Forward and expanded upon by others in designs for so-called black hole starships. In one version, a spacecraft carries a Kugelblitz in a containment field and uses the emitted radiation as propellant. The radiation is directed rearward using a high reflectivity parabolic mirror, an impossible feat with current materials, but potentially viable with future technology. The radiation, being made of massless photons, exerts pressure. And with enough of it, the pressure becomes thrust. This isn't chemical thrust. This is relativistic propulsion. The kind of drive that could, in theory, accelerate a spacecraft to a significant fraction of the speed of light. And it gets better. The smaller the black hole, the more intense its radiation, and the more powerful the thrust. Some futuristic designs even imagine ships that feed the Kugelblitz, injecting mass or energy into the black hole to keep it stable and extend its lifespan. Others imagine swarms of small Kugelblitzes used like energy coins, dropped into star systems to power stations, satellites, or even entire cities. These black holes wouldn't be massive enough to threaten their surroundings, but just large enough to provide steady output for years, centuries, or millennia, depending on their mass. In these visions of the future, humanity doesn't just extract energy from stars, we build artificial ones. Black holes become the new fusion reactors. And the ultimate fuel isn't uranium, hydrogen, or antimatter, it's focused light, collapsed and frozen in time. But this leads to technical challenges so daunting they border on the mystical. To use a Kugelblitz as a power source, you must be able to create it, contain it, and convert its radiation into usable forms of energy or thrust. That means building materials that can withstand temperatures in the billions of degrees. It means controlling magnetic or gravitational fields with precision beyond anything humanity has yet achieved. It means understanding how radiation behaves in the curved spacetime near an event horizon, and harvesting that energy without letting the black hole escape its prison. The containment itself might involve metastable energy shells, negative mass ring structures, or quantum field traps, concepts that still live only in theoretical papers. Some even propose creating a Kugelblitz inside a warp bubble, allowing a spacecraft to carry it without experiencing its full gravitational effects. In another variation, the Kugelblitz is kept stationary in space, surrounded by an energy capture array, something like a Dyson swarm, but focused on high-frequency radiation rather than starlight. The radiation is converted into usable electricity and beamed wirelessly to spacecraft or planetary colonies. A Kugelblitz power station floating in interstellar space could become a beacon of civilization, a pinprick of darkness radiating life. The possibilities stretched beyond propulsion and power. A controlled Kugelblitz could be used to bend light and time, creating isolated regions of altered physics. One could imagine laboratories that study quantum gravity, or time-dilated vaults where centuries of external time pass in seconds internally. Or even communication relays that send signals curved through warped spacetime. But perhaps the most exciting possibility of all is using a Kugelblitz as the key to interstellar travel. No known propulsion system can take a human vessel to another star in less than decades, unless you can manipulate spacetime itself. And some speculative proposals suggest that Kugelblitzes, being compact and intensely energetic, might serve as the anchor points for wormholes or warp drives. In these models, the black hole is no longer just a power source, it becomes the fabric through which space is threaded. A drive not powered by the black hole, but made from it. It's here that the line between science and magic blurs. Kugelblitzes, born from light, could become the chariots of civilization. Portable engines, power cores, gravitational tools. If an advanced species learns to wield them, they would cross the galaxy not by burning fuel, but by sculpting spacetime. And to think, it all begins with a flash of light, focused so tightly that time itself gives way. A Kugelblitz, a black hole made entirely of light, begins its existence not with the collapse of matter, but with the triumph of energy density. A singular, immense pulse of radiation so intense, so tightly confined, that spacetime itself is forced to bow. An event horizon forms, and light becomes its own undoing. But what happens after that moment? Once the Kugelblitz is born, what if you keep feeding it? Not with matter, but with more light? The answer is elegant and profound: it grows. Black holes don't care what you feed them. Matter or energy, atoms or photons, it all contributes to the total mass energy content trapped within their horizon. So yes, if you continue directing energy, in the form of high-powered radiation, laser pulses, or even cosmic rays, toward a kugelblitz, it will increase in mass. Its event horizon will expand. Its gravitational pull will deepen. And its presence in the fabric of space-time will grow more profound. In many ways, a kugelblitz behaves just like a traditional black hole once formed. The difference is in how it started, not in how it behaves afterward. It may have been forged from pure radiation, but the laws of general relativity don't distinguish what kind of energy caused the singularity. From that point on, it becomes an energy sink, and light is just more fuel. Imagine this process like stoking a fire, but in reverse. You're not adding logs to flames. You're adding fire to a void, and watching that void deepen. If you shine more light into the kugelblitz, incredibly intense, coherent, focused radiation, it doesn't reflect. It doesn't scatter. It doesn't bounce back. It falls inward, curving along the warped paths of spacetime until it disappears past the event horizon. And as it vanishes, the total energy inside the black hole increases. That increase has real, observable consequences. The Schwarzschild radius, the distance from the center to the event horizon, expands. The black hole becomes larger, more massive, and its gravitational influence stretches further outward. From an external observer's perspective, it appears as if the kugelblitz is swallowing the light, converting pure radiation into gravitational growth. But there's a subtle twist. Light is massless, yet it still carries energy and momentum. When it falls into a black hole, it contributes to that black hole's mass not by adding physical substance, but by increasing the total curvature of spacetime trapped inside. This is why, paradoxically, a black hole made from nothing but photons can still have mass. Mass, in the context of relativity, is energy. And energy is mass. Feeding more light into a kugelblitz is no different than dumping neutron-rich matter into a stellar black hole. The energy inside simply climbs higher. So how much light would you need to noticeably grow one? That depends on its current size. A kugelblitz with the mass of a small mountain would require astronomical amounts of radiation to double in size. We're talking about more energy than a star emits in centuries. But if your civilization has access to focused solar output, antimatter production, or direct manipulation of high-energy fields, it might become a viable, even routine, method of black hole cultivation. One could imagine a civilization creating small kugelblitzes, then carefully feeding them energy over time to grow them into larger ones, each with custom properties. A tiny black hole for powering a satellite. A medium one for interstellar propulsion. A massive one stored in isolation, waiting to act as a gravitational anchor or energy bank. And there's no reason the feeding process has to be continuous. You could release energy in pulses, focused laser bursts, electromagnetic compression waves, or even matter converted to radiation and then streamed into the kugelblitz from afar. Each pulse would be absorbed, each increment contributing to growth. But here's the fascinating paradox. The more you feed the kugelblitz, the cooler it becomes. According to Hawking radiation theory, smaller black holes radiate faster. They emit more energy, and they have higher surface temperatures, though surface is an abstract term here, since black holes have no actual surface. But as a black hole grows, its temperature drops. It radiates more slowly and becomes more stable. So by feeding a kugelblitz more light, you are effectively extending its lifespan, making it less prone to rapid evaporation. A micro-kugelblitz might evaporate in seconds, screaming out gamma rays in a final burst of high-energy death. But a larger, more massive one, fattened by constant feeding, could persist for eons. It would become cooler, quieter, more enduring. So a growing kugelblitz isn't just more massive, it's more useful, more manageable, and paradoxically, less volatile. This creates a fascinating technological balance. Too small, and the kugelblitz is unstable, a fiery candle burning too hot to contain. Too large, and it becomes sluggish, difficult to manipulate, a cold monolith of compressed light. But just right, and it could become the perfect engine, the perfect battery, the perfect prison. There's also a deeper implication. If we imagine a future where civilizations sculpt these objects, they may create entire farms of kugelblitzes. Arrays of black holes suspended in stasis, being steadily fed beams of energy from stellar harvesters. Each one growing in controlled increments. Some for propulsion. Some for computation. Some for experimentation. Light is pumped in, and mass emerges. From energy comes gravity. From photons, a singularity. From light, darkness. Feeding a kugelblitz isn't just a method of growth. It's an act of cosmic alchemy, a transformation of motion into stillness, of waves into wells. It's the universe's most paradoxical recipe: add more light, and make the dark even deeper. Containing a black hole, especially one born from light itself, is perhaps one of the most mind-bending engineering challenges in all of speculative science. A kugelblitz, by its nature, is a gravitational singularity formed from the ultimate freedom, radiation. You don't trap it in a cage, it is the cage. It traps light, matter, time, everything. And yet, if you intend to use it for propulsion, power, or experimentation, you must contain it. Not just stop it from escaping, but stop it from consuming the very fabric of your ship, station, or world. So the question becomes, how do you confine the uncontainable? First, we must address a critical truth. You can't build a physical wall around a kugelblitz. Not in the traditional sense. You can't wrap it in steel or confine it in a vacuum chamber. Anything that gets too close will simply be swallowed. Not metaphorically, but literally, consumed by its event horizon and lost to the singularity. So containment must happen at a distance. The kugelblitz has to be isolated in space, suspended in equilibrium, kept far from any mass or energy source it could absorb. One speculative method is the use of a gravitational cage, a carefully balanced configuration of massive objects or artificially generated gravitational fields arranged around the kugelblitz to hold it in place. This wouldn't work by resisting its pull, but by balancing it. Imagine a three-dimensional arrangement of artificial gravity generators, orbiting masses, or controlled dark matter anchors, all perfectly positioned to create a neutral, gravitational pocket, where the kugelblitz can remain suspended in stasis. If it drifts too far in one direction, opposing forces pull it back into place. Like a marble floating in the center of a carefully curved bowl, except the bowl is made of warped spacetime, and the marble is a hole in reality. Another containment strategy involves dynamic equilibrium via radiation pressure. Although it sounds paradoxical, radiation can exert a push, a form of pressure, when it strikes a surface. If your civilization can generate directed radiation of sufficient intensity, it may be possible to push back against the kugelblitz using beams of light, finely tuned and focused. These wouldn't prevent escape, because the kugelblitz isn't trying to escape, but they could stabilize its position, nudging it away from danger, like tractor beams made of firelight. This requires constant, real-time adjustment, adaptive systems that monitor the black hole's position, velocity, and energy output to ensure it never drifts toward anything critical. But radiation pressure is incredibly weak per photon. So a more robust method might involve electromagnetic containment, though not in the usual way. A traditional black hole, formed from matter, has no charge. But a kugelblitz, if designed deliberately, might be formed using polarized or charged radiation, potentially granting it an overall electric or magnetic field. This is purely speculative, but if achievable, it opens up the possibility of suspending the kugelblitz within a magnetic bottle, a structure akin to the plasma traps used in fusion reactors, but designed for gravitational singularities. Think of a magnetic field shaped like a perfect sphere or torus, held in place by superconducting rings and quantum stabilizers, cradling the black hole like a pearl in a storm. The black hole's event horizon never touches the walls, it hovers, suspended by invisible arms of geometry. This method, while wildly beyond our current abilities, could offer both containment and control, allowing for precise manipulation of the kugelblitz's position and energy interaction. Some theorists also speculate on the use of negative energy fields. If such fields exist, and quantum physics suggests they might, in the form of exotic matter or Casimir effects, they could provide a means to repel gravitational mass, essentially counterbalancing the pull of the black hole with an engineered push. Negative energy could, in theory, create a spacetime bubble in which the black hole is isolated from the external universe. Inside that bubble, the laws of gravity would bend differently, perhaps even neutralizing the black hole's reach. Such technologies would also be a prerequisite for warp drives and wormholes, making them a logical frontier for a civilization already tinkering with kugelblitzes. Then there's the idea of photon reflectors, not as containment per se, but as an interface. These wouldn't stop the black hole, but they could allow interaction with it. Imagine a high-fidelity reflector system positioned around the kugelblitz, not to bounce light out, but to focus radiation in. You could feed it energy, carefully, precisely, through this array. And if you're harvesting Hawking radiation, these same systems could channel the emitted particles outward, guiding their energy flow into conversion modules for electricity or thrust. Reflectors in this context act like valves, not walls, tuning the flow of information between light and darkness. But the real masterpiece of containment may lie in space-time engineering itself. A civilization that can create a kugelblitz might not need to contain it in the traditional sense. Instead, it could embed it in a stable curvature, a pocket universe, a folded dimension, a localized wormhole tunnel with its own self-contained physics. The kugelblitz exists, but only within a bubble where it cannot affect the larger cosmos. Think of it like a fish in a self-sustaining aquarium floating inside a lake. The lake isn't affected, only the bubble is. This quantum bottle, or dimensional cocoon, would act as both shield and interface. You could observe the black hole, feed it energy, harvest its output, all without ever exposing your world to its gravitational reach. It's not science fiction in the traditional sense. It's science extrapolated forward to its most outrageous limits. Of course, all of this is theoretical. There's not even consensus yet on whether tiny black holes could be made or controlled, let alone sustained or caged. But physics allows us to ask the questions and speculate on the answers. If such containment systems could be developed, kugelblitzes could be used with precision. Suspended aboard spacecraft, they could become engines. Embedded in space stations, they could become reactors. Mounted in orbital arrays, they could power entire civilizations with the gentle, deadly heartbeat of pure gravity. But containment is not just about engineering. It's about responsibility. A kugelblitz left unchecked could drift. It could grow. It could consume. It doesn't care about moral boundaries. It doesn't care about mistakes. It's a prison of light, hungry for more. If you drop the cage, even once, the consequences could last for centuries. Or never end. And yet, for a civilization wise enough to play with the tools of creation, and careful enough to respect them, the kugelblitz could be the most powerful instrument in the cosmic toolbox. Contained not with walls, but with understanding. If a kugelblitz is formed from pure light, not matter, if it is energy collapsed into a singularity, not atoms crushed into oblivion, does that change the rules of the universe? At first glance, you might think so. After all, there's no matter to be crushed, no protons or neutrons to be lost, no atoms to disappear into the void. It's just photons. Informationless, massless, featureless beams of radiation. But here's the twist. Even a kugelblitz isn't free from the universe's deepest and most haunting mystery, the black hole information paradox. To understand the stakes, we have to revisit the original puzzle. According to general relativity, once anything crosses the event horizon of a black hole, it's gone, hidden forever from the rest of the universe. This is fine on its own. General relativity is all about what happens to mass and spacetime. But quantum mechanics tells a very different story. Information must never be lost. It's not just a philosophical stance, it's a foundational law of physics. The quantum state of any particle, however complex or trivial, must be preserved in some form, even if that particle falls into a black hole. This brings us to the paradox. When matter, say, a star, collapses into a black hole, all the information about its structure, the quantum states of its particles, its exact shape and makeup, is seemingly lost. The resulting black hole is described by only three properties: mass, charge, and spin. Everything else is wiped clean. When the black hole eventually evaporates through Hawking radiation, that radiation appears to be completely random. It contains no imprint of the star that formed it. The information, it seems, has vanished. But that can happen. Not if quantum mechanics is right. So what does this mean for kugelblitzes? Black holes form not from complex matter, but from energy. Does the paradox still apply? Surprisingly, yes. And here's why. Photons carry information too. Even though light is massless, it's not meaningless. Photons can be polarized. They have frequency, direction, spin. A beam of light isn't just a stream of identical particles. It's a structured wave of electromagnetic fields, rich with information. In fact, we use light to carry information across the world every day: fiber optics, radio waves, laser communication. Photons are the carriers of information in our civilization. So if you concentrate a massive amount of light into a point and create a kugelblitz, you are not creating an information-free black hole. You're creating one with potentially incredible complexity, because you could, in theory, program that light, modulate it, and code data within its polarization, intensity, phase relationships. The resulting black hole would appear simple on the outside, but it would be born from complexity. That leads to a startling realization: a kugelblitz, like any black hole, carries hidden information within. The photons that formed it may no longer exist individually, but the structure of their energy, the pattern of their collapse, might be preserved, somehow, within the fabric of the singularity. But if the black hole eventually evaporates via Hawking radiation, and that radiation is purely thermal, we're right back where we started. The information is lost. And that breaks the laws of quantum mechanics. This is the Kugelblitz information paradox, a variant of the same riddle that plagues all black holes, only now sharpened by the knowledge that the origin was energy, not mass. Because we can design the initial energy input with precision, the information loss becomes even more apparent. Physicists have proposed many solutions to this dilemma, and every one of them applies equally to kugelblitzes. One idea is that information is stored on the event horizon in a two-dimensional form, a theory called the holographic principle. In this view, everything that falls into a black hole leaves an imprint on the surface, like data burned onto a disk. Hawking radiation, over time, slowly encodes that data and releases it back into the universe in subtle, scrambled form. If this is true, then even a black hole made entirely from light would leave its fingerprint on the horizon. And as it evaporates, those fingerprints would be gradually revealed. Another idea is that black holes don't destroy information, they teleport it to a parallel universe, or a baby universe that branches off inside the singularity. This theory preserves quantum mechanics, but at the cost of causal closure. The information isn't lost, but it's gone from our reality forever. That's hardly satisfying for physicists who want to preserve predictability within our universe. A third possibility is that Hawking radiation isn't random, it only seems that way. Over time, subtle quantum correlations between emitted particles could contain encoded data, effectively leaking the black hole's secrets back into space. But this would require an almost miraculous level of hidden order in what we thought was pure thermal noise. Yet another suggestion is that firewalls exist at the event horizon, searing sheets of high-energy particles that obliterate information before it can be lost. But this violates another principle, the equivalence principle, which says that crossing a black hole's event horizon should feel like nothing special. Firewalls introduce a brutal disruption to that idea, and to the smooth geometry of general relativity. Still, others argue that perhaps black holes never form at all, at least not in the traditional sense. The process of collapse, they say, takes infinite time from an external viewpoint, meaning information is never truly trapped. But this sidesteps the reality that black holes do form and do influence the universe around them. So where does this leave the kugelblitz? Exactly in the heart of the storm. It doesn't escape the paradox, it makes it more personal. Because unlike stellar black holes, which arise from messy, unpredictable processes, a kugelblitz can be engineered. Its energy input can be precisely controlled, even encoded like a cosmic QR code. You could, in theory, make a black hole from data, a singularity whose collapse contains instructions, messages, patterns. And then ask, does the universe remember? If we fire highly structured beams of polarized light into a point until a black hole forms, and then wait for billions of years as it evaporates, will the resulting Hawking radiation mirror the original signal? Will we receive, across the eons, a faint echo of the input? Or will it all be noise? This has profound implications for communication, cosmology, and even consciousness. Because it forces us to consider what a black hole really is, an information process, not just a gravity well. And if light can carry memory, then a kugelblitz may be a vessel of lost history, a sealed book, waiting for its pages to be read again. The paradox endures. It haunts every black hole, no matter how it was born. And until we unlock the code, until we find the language hidden in the radiation, we are left with a troubling truth. Even light, when turned inward, can forget. When we think of light, we think of something pure, radiant, massless, free. We don't associate it with heat or disorder in the same way we do with matter. But collapse light into a kugelblitz, and the rules of the cosmos twist in on themselves. That which once illuminated now devours. And somehow, impossibly, thermodynamics still applies. The thermodynamics of black holes, even those made of light, is one of the most fascinating intersections between gravity, quantum mechanics, and statistical physics. It reveals a deeper truth: black holes aren't just gravitational objects. They're thermodynamic systems. And that includes kugelblitzes. Let's start with the most famous property: temperature. A kugelblitz, once formed, radiates energy just like any other black hole. This phenomenon, Hawking radiation, emerges from the strange dance of quantum particles at the edge of the event horizon. Virtual particles briefly blink into existence in pairs. Normally, they annihilate instantly. But near a black hole, one can fall in while the other escapes. To an outside observer, it looks as if the black hole is emitting particles. This radiation gives the black hole a temperature, one inversely proportional to its mass. So the smaller the black hole, the hotter it gets. This is where the story becomes wild. A kugelblitz with the mass of a mountain might have a temperature in the range of billions of degrees, far hotter than the core of any star. If it's even smaller, say the mass of a building, it could reach temperatures in the trillions of degrees. These temperatures aren't just theoretical curiosities. They determine how quickly the black hole evaporates. The hotter it is, the faster it radiates. For tiny kugelblitzes, this process could take seconds, milliseconds, or less. But the most profound thermodynamic property of a black hole, and yes, of a kugelblitz, is entropy. In classical thermodynamics, entropy is a measure of disorder, the number of possible microscopic arrangements of a system. For something like a gas, it's easy to imagine all the molecules flying around in countless combinations. But a black hole? It seems like the ultimate simplicity, just mass, spin, and charge. And yet black holes, despite their simplicity on the outside, have staggeringly high entropy. In fact, the entropy of a black hole is proportional not to its volume, as you might expect, but to the surface area of its event horizon. This is the famous Bekenstein-Hawking entropy formula, which showed that the entropy of a black hole increases with the square of its radius. This idea was shocking when first proposed. How could something so small, a point of infinite density, have so many possible internal states? The answer seems to lie in the nature of information. A black hole's entropy might represent the total number of ways that the material, or radiation, that formed it could have been arranged. In other words, it encodes all the lost information inside. This brings us back to kugelblitzes. Even though a kugelblitz is born from radiation, not matter, the entropy still exists. Photons can be organized in countless ways, varying in frequency, polarization, timing, direction, and coherence. If a kugelblitz forms from highly structured light, its entropy might reflect the richness of that original structure. If it's made from a chaotic flood of gamma rays, the entropy may be even higher, a perfect thermal mess. But here's the strange twist. The entropy of a black hole is the maximum possible entropy any object of that size can have. Nothing can be more disordered, more information dense, than a black hole. This makes it a kind of thermodynamic ceiling, the upper limit of confusion. The universe can't be more uncertain than a black hole. And that includes a kugelblitz. This raises a stunning implication. The process of creating a kugelblitz, focusing vast amounts of radiation into a single point, is not just a feat of energy concentration. It is also a feat of information compression. It's the act of packing as much entropy as possible into the smallest possible boundary. Light, once orderly or chaotic, becomes something else entirely. A structure that appears simple, just a sphere in space, but that hides the most complex arrangement of states the universe allows. This complexity leads to one of the great questions of modern physics. What happens to that entropy when the kugelblitz evaporates? If Hawking radiation is truly random, the entropy vanishes, and with it, all memory of what the black hole once was. But if information is preserved, then that entropy must somehow be released, coded into the radiation itself. This is where thermodynamics becomes a battleground for quantum gravity, string theory, and the holographic principle. Another key aspect of thermodynamics is the second law, which says that entropy in a closed system always increases. Black holes fit this perfectly. You can't reduce a black hole's entropy, not without violating fundamental principles. Throwing more matter or light into a kugelblitz makes it larger and hotter. It gains more mass, and with it, more entropy. In fact, merging two black holes, even two kugelblitzes, results in a new black hole whose total entropy is greater than the sum of the originals. It's the cosmic version of irreversible disorder. And there's more. Black holes also have heat capacity, though it's negative, a truly bizarre feature. Most objects heat up as they gain energy. But small black holes cool down as they absorb more mass. This makes their thermodynamics fundamentally unstable. A tiny kugelblitz, if not carefully fed, might explode in a final burst of evaporation. A larger one, given just a little more energy, might stabilize for billions of years. In this light, kugelblitzes, pun very much intended, become thermodynamic machines. You could theoretically build systems that extract energy from their temperature gradients, store entropy in their structure, and manage heat flows at the scale of spacetime itself. And yet they remain enigmas. They obey the same rules as matter-born black holes, yet they offer a cleaner laboratory, a simpler origin story, a controllable structure. In a way, they are the ideal test subjects for studying the deepest laws of thermodynamics. No messy fusion cores, no turbulent stellar collapse, just energy and gravity, in pure, distilled form. They are black holes, but born of radiance, not ruin. And in their cold, dark hearts, they hold more heat, more disorder, and more secrets than any furnace ever known. In the earliest instance of our universe, before the first atom, before the first proton, even before the first quark had fully settled into its existence, there was only energy. The newborn cosmos was a seething ocean of unimaginable temperatures and densities, a place where matter had not yet coalesced, and space and time were only beginning to stabilize. It was a universe of pure radiation, unfiltered, unrestricted, and everywhere. This era, known as the radiation-dominated epoch, may have been the most violent and chaotic period in all of cosmic history. And in that chaos, that raw bath of overlapping photons, neutrinos, gluons, and high-frequency gravitational waves, something astonishing may have happened. It is entirely possible that kugelblitzes formed naturally, spontaneously birthed from the wild fluctuations of energy density in the early universe. To understand how, we need to go back to the conditions of the first fraction of a second after the Big Bang. Temperatures were so high that energy existed in the form of radiation, not just visible light, but gamma rays, X-rays, and other exotic, ultra-high-frequency modes. Matter hadn't yet condensed. There were no stars, no atoms, no elements, just fields and force particles bouncing in every direction. The density of energy per cubic centimeter exceeded anything we can reproduce in labs today. In fact, it surpassed the energy output of entire galaxies in microscopic volumes. Now imagine a momentary fluctuation, a rare event in which just enough energy, perhaps even by sheer statistical accident, was concentrated into a small enough region. No matter, just light. And yet that light was so densely packed that it bent space-time inward. Gravity, responding not to mass but to energy, curved space so tightly that an event horizon formed. A black hole, made purely from radiation, was born. A primordial kugelblitz. These wouldn't be like the enormous black holes at the centers of galaxies or even the massive stellar remnants from supernovae. These would be tiny. Some may have had the mass of a mountain squeezed into the volume of an atom. Others might have had the mass of a car packed into something smaller than a proton. And a few, the rarest of the rare, may have been large enough to persist to this very day. Because here's the twist: small black holes evaporate fast through Hawking radiation. The smaller they are, the quicker they vanish. A micro-kugelblitz formed seconds after the Big Bang might have lasted only a blink before exploding in a flash of high-energy radiation. But a slightly larger one, just a bit more massive, could take billions of years to evaporate. Some may still be out there now, roaming the universe as relics of the radiation age. In fact, some cosmologists believe that if primordial black holes, including kugelblitzes, formed in large numbers, they could account for part of the dark matter that we observe today. These tiny, ancient, invisible objects would drift through the cosmos without emitting light, interacting only through gravity. They'd be dark, massive, and everywhere, perfect candidates for the mysterious missing mass that tugs on galaxies and distorts spacetime across the universe. And if these primordial kugelblitzes do exist, we might even be able to detect them. They'd be difficult to spot, to be sure. Tiny black holes emit very little Hawking radiation unless they're at the final moments of their life. But if one were to evaporate near us, perhaps in a neighboring region of our galaxy, it would produce a sudden, brief, incredibly intense burst of gamma rays. These gamma ray bursts, which we occasionally detect from deep space, are still not fully understood. Could some of them be the dying screams of ancient kugelblitzes, evaporating after billions of years of solitude? It's a tantalizing possibility. And what about the impact these kugelblitzes could have had on the early cosmos? During the first seconds after the Big Bang, their formation might have seeded gravitational wells, influencing the distribution of matter as it began to cool and condense. Even though they were made of light, their gravity would attract matter once it formed. They could have helped shape the large-scale structure of the universe, acting as hidden architects of the cosmic web. Moreover, the gravitational waves produced by their formation, sudden, intense ripples in spacetime, would still be echoing through the cosmos today. If we had sufficiently sensitive detectors, tuned to the right frequencies, we might even hear the faint whispers of these ancient events. Not light, not particles, but the very trembling of the universe as it tried to contain the most intense flashes of energy ever seen. Some researchers have proposed that the formation of primordial black holes, including kugelblitzes, could be connected to brief periods of cosmic inflation or symmetry breaking, moments when the laws of physics themselves shifted slightly. During these transitions, energy densities could spike locally, triggering the spontaneous birth of black holes without any matter involved. These would be cosmic fossils, older than atoms, older than galaxies, perhaps even older than the constants of nature as we know them. Studying them would be like digging into the first sentence of the universe's origin story. And here's the poetic part: light, the thing we associate with birth, clarity, and openness, could have been the very first cause of cosmic death. Before stars lived and died, before anything solid had ever existed, light may have collapsed into itself, carving gravitational scars into the newborn cosmos. From this perspective, kugelblitzes are not just hypothetical constructs. They are echoes of the universe's infancy, forged in the raw fire of creation, possibly still wandering the cold corridors of space, unseen, undetected, misunderstood. They are reminders that even in a universe dominated by energy, gravity listens. It does not care whether energy comes from mass or from light. If it is focused enough, intense enough, curved enough, the result is the same: a hole in the fabric of being. A darkness born of brilliance. In the age of high-energy physics, where colliders smash protons together at nearly the speed of light and lasers generate fields stronger than those found near neutron stars, the boundary between theoretical and experimental science grows thinner every year. And so the question arises, could we simulate a kugelblitz in the lab? Could we take beams of coherent light, perhaps the most well-understood and controllable form of energy in our modern toolkit, and push them so far, so tightly, so violently, that they mimic the gravitational collapse of radiation into a miniature black hole? It's a question that dances on the edge of the impossible. And yet, it's being asked? The fundamental principle behind a kugelblitz is simple in theory. If you concentrate enough energy into a small enough region of space, the energy density curves spacetime so intensely that it forms an event horizon. And since light is energy, sufficiently intense light, packed and focused to extraordinary extremes, should, in principle, collapse into a gravitational singularity. That's the logic. But can lasers really deliver that kind of energy? Let's look at the numbers. To form a kugelblitz the size of a grain of sand, you would need to focus more energy than a typical nuclear arsenal could ever provide. In fact, even the most advanced fusion reactions humanity has developed don't come close to producing the necessary energy densities. The kind of energy required is astronomical. We're talking about converting the mass energy equivalent of an asteroid or a small moon into focused radiation, compressed into a microscopic volume within a fraction of a second. That said, technology is advancing rapidly. Modern petawatt-class lasers, like those used in inertial confinement fusion experiments, already generate short bursts of light with more power than the entire electrical output of some nations. These beams are brief, yes, but they are concentrated. In places like the National Ignition Facility in the United States, or the Extreme Light Infrastructure, ELI, in Europe, scientists are beginning to probe the behavior of matter and fields under truly extreme conditions, inching toward the kinds of environments where spacetime itself might begin to bend. Still, forming a real kugelblitz, even a tiny one, remains far beyond our reach. So the idea shifts. What if we simulate one instead? Not by collapsing spacetime itself, but by mimicking the behaviors and interactions that would occur if we could. Enter the field of analog gravity. Physicists have begun exploring systems in which the mathematics describing waves and fields in a medium mirror the equations of general relativity. For instance, in certain fluid flows, sound waves behave similarly to how light would act near a black hole. These systems are called acoustic black holes, or dumb holes, not because they lack intelligence, but because sound cannot escape from within their equivalent of an event horizon. Likewise, in optics, researchers have explored optical analogs of event horizons using nonlinear materials, substances in which intense light alters the medium through which it passes. In these setups, a pulse of high-intensity light can create a changing refractive index, effectively trapping slower light pulses behind it, similar to how gravity traps light in a black hole. It's not a kugelblitz in the literal sense. There's no gravitational collapse, but it's a proxy, a way to explore some of the physics using available tools. In even more advanced experimental proposals, scientists imagine focusing multiple high-powered laser beams into a single microscopic point in space, possibly inside a vacuum chamber surrounded by mirrors or magnetic fields. The idea would be to reach such an absurd energy density that the quantum vacuum itself begins to behave differently, perhaps even allowing particle pairs to form, or light to scatter off light, a phenomenon known as photon-photon scattering. This phenomenon, long predicted by quantum electrodynamics, QED, only becomes measurable at extreme energy densities. In effect, these interactions begin to reveal the nonlinear structure of the vacuum, the boiling nature of empty space. Could these effects, pushed to the limit, eventually reproduce the beginnings of a gravitational response? Some researchers believe it might be possible to detect gravitational lensing effects from intense light pulses, though the distortions would be so small as to require instrumentation of extraordinary precision. Others are exploring the idea of plasma mirrors, dense sheets of ionized particles that reflect and amplify light beyond traditional optical limits, enabling tighter focusing and higher intensities. The hope is that through careful design, these systems could edge closer to the energy concentration thresholds needed to mimic gravitational collapse. Another avenue is the use of ultra-intense short-pulse lasers in combination with high-energy particle accelerators. Imagine using lasers to create a dense photon field, while colliding high-energy particles into the focal point. This hybrid approach could, in theory, create a localized energy spike intense enough to probe effects predicted by quantum gravity, even if not enough to create an actual Kugelblitz. And what if we take a leap forward, into science fiction for a moment? Suppose an advanced civilization, one capable of harnessing the total output of a star, develops a Dyson sphere-scale structure capable of collecting and directing light. They build a vast optical collider in space, using enormous mirrors and gravitational lensing to focus radiation from across their solar system into a singularity. Not metaphorically, literally. The system is tuned down to the nanosecond, synchronized across millions of kilometers, until trillions upon trillions of photons strike a point in perfect unison. The structure folds light into itself, and for a heartbeat, a Kugelblitz is born. An artificial black hole, formed not from the death of stars, but from the weaponization of starlight. It evaporates in a flash. Or they contain it. Use it. Harness it. Back on Earth, we're nowhere near that capability. But we are building tools to understand how radiation behaves at its extremes. We're studying light not just as a wave or particle, but as a substance, something with weight, power, and the potential to reshape the very vacuum from which it arises. Each experiment with ultra-intense lasers is a step closer. Not necessarily to making a Kugelblitz, but to understanding the boundary, the line between the linear world we know, and the nonlinear regime of space-time warping. In the end, simulating a Kugelblitz may teach us more than creating one. It could reveal how light interacts with itself, how energy curves the vacuum, how quantum fields respond to extremity. And in doing so, it may illuminate the final piece of the puzzle, how to unite gravity and quantum mechanics. From the smallest lab-scale experiments to the grandest cosmic structures, it all comes down to a single idea. Light is not weak. It is not passive. It is the most concentrated, versatile form of energy the universe has ever known. If anything can unlock the secrets of singularities, it may not be matter. It may be light. Imagine, for a moment, that the world's most advanced scientific minds succeed. After decades of pushing the boundaries of photonics, quantum electrodynamics, and gravitational theory, they build the ultimate experimental machine, a device capable of focusing unimaginable amounts of energy into a point, enough to collapse light into gravity itself. After meticulous calculations, redundant safety systems, international oversight, and ethical debates stretching over generations, the countdown begins. This is not a test of nuclear force. It's something new. Something primal. The forging of a Kugelblitz, a black hole born not from stars, but from the deliberate precision of humanity's light. What happens next? If a Kugelblitz were actually created on Earth, even a minuscule one, the implications would be as profound as they are terrifying. The first factor that determines what follows is its size, or more precisely, its mass-energy equivalent. Let's say the experiment successfully focuses just enough energy to create a Kugelblitz with the mass of a small mountain, approximately kilograms. At that mass, it would be microscopic, far smaller than an atom, but its gravitational pull would be extreme. It would radiate Hawking radiation, yes, but at a rate inversely proportional to its mass, meaning this particular Kugelblitz might evaporate slowly, over millions of years. In that time, it would be capable of pulling in atoms, molecules, perhaps even the structure surrounding it. This version would be devastating, not because it explodes, but because it feeds. Slowly, invisibly, relentlessly. If not perfectly contained, it could begin absorbing matter in its vicinity, growing steadily, becoming hungrier. In a few years, it might devour a lab. In a century, a city. Left unchecked for long enough, it could become an unstoppable gravitational cancer at the heart of the planet. But maybe the scientists knew this. Maybe the experiment was scaled down to something truly minuscule. Perhaps the Kugelblitz formed carries the mass energy of a small object, a few kilograms, or even less. In that case, its Hawking radiation would be intense, and it would evaporate in microseconds. Such a brief existence would cause a massive release of gamma radiation, enough to annihilate everything in the immediate vicinity. Think of it, an invisible, subatomic flashpoint in space, a singularity that lives and dies in the span of a blink, but radiates more energy than a nuclear warhead. No fallout, no mushroom cloud, just a sudden, blinding silence. The danger here isn't just gravitational. It's thermonuclear level energy without the warning signs. A kugelblitz created in the wrong place could obliterate everything within kilometers before sensors even register its birth. In a worst-case scenario, it could punch a hole in the planet, not through mass, but through extreme gamma rays and the destabilization of matter on a quantum scale. So what kind of safeguards would be needed to even attempt this? First, the experiment would need to take place nowhere near Earth. Think deep space, perhaps on a moon base, or even a massive station placed in a high Earth orbit shielded by layers of advanced material. Containment wouldn't be mechanical. You can't put a cage around a black hole. It would require a vacuum field, with zero nearby matter. Lasers creating the kugelblitz would have to be fired in from far outside the target zone to ensure that no apparatus is drawn into the event horizon by accident. The system would also need real-time quantum sensors to monitor the emergence of the event horizon and determine the exact lifespan of the kugelblitz. If it begins to last longer than expected, or feed on surrounding virtual particles, automated kill switches would instantly terminate the energy input and trigger counter-radiation pulses to destabilize the focus point. Even more daring would be the creation of a kugelblitz trap, a spherical cage of photon mirrors or gravitational wave generators designed to keep the singularity from drifting. This is speculative, deeply so, but if light can collapse into a black hole, perhaps its mirror opposite could help contain it. But suppose everything goes right. The device activates. The beams align. For a fraction of a nanosecond, space-time ripples, and light becomes something more. Instruments scream with data. Sensors detect curvature where none existed. Space has collapsed into itself, not with the crushing weight of a dying star, but with the precision of focused radiance. A perfect kugelblitz. And then, moments later, it's gone. Not failure. Not disaster. But success. The Earth remains. The lab, shielded in deep space, is intact. And the implications ripple outward like the shockwave that never came. We have touched the fundamental machinery of the cosmos, bent reality with the force of light alone. We have proved that energy alone, the very same stuff that powers our phones, our stars, our breath, can become gravity incarnate. The world would never be the same. Philosophers would write of light devouring itself. Engineers would dream of black hole drives and infinite batteries. Physicists would pore over the data for generations, asking what spacetime really is when even light can be its architect. And the public? They would marvel at the fact that the most destructive force in existence, the black hole, could be created not through chaos, but through the most orderly form of energy ever known, the laser. A beam of perfect light, aimed with perfect focus, for a perfect purpose. A kugelblitz born on Earth. And perhaps, born again. If black holes are the great puzzles of physics, then kugelblitzes are the cleanest, sharpest pieces of the whole cosmic mystery, stripped of the messy complexity of matter, forged instead from pure light. And in the precision of their theoretical simplicity, they may offer something extraordinary, a pathway into one of the greatest scientific quests of all time, the unification of general relativity and quantum mechanics. This quest isn't new. Physicists have spent more than a century trying to merge Einstein's theory of gravity, which governs planets, stars, galaxies, and the curvature of spacetime, with quantum field theory, which controls the behavior of particles, forces, and the chaos of the subatomic realm. These two descriptions of the universe have been remarkably successful in their domains. But when you try to apply both at once, say, at the singularity of a black hole or during the Big Bang, the math breaks down. The equations stop making sense. Singularities appear. Infinities crop up. Nature, it seems, refuses to speak both languages at the same time. Yet that's exactly what black holes demand. They are formed by gravity, described by Einstein. But they evaporate through Hawking radiation, a quantum process. They store information, or destroy it, in a way that challenges both thermodynamics and causality. They are bridges to paradox, playgrounds of impossibility. They force physicists to confront a brutal fact: our two greatest theories are incomplete. Now, imagine if we had a type of black hole that didn't come from collapsing stars or crushing matter, but from energy alone, light, concentrated to the point of gravitational collapse. This is the Kugelblitz, and its simplicity may be its greatest gift to science. Traditional black holes are complex in origin: the death of massive stars, chaotic gravitational interactions, accretion disks, rotation, magnetic fields. There's an inherent messiness to them. A Kugelblitz, by contrast, arises from the cleanest possible condition: energy concentrated into a region so dense that gravity takes over. No neutrons. No quarks. No fusion remnants. Just the raw curvature of spacetime in response to light. Because of this purity, Kugelblitzes are a near-ideal laboratory for testing ideas in quantum gravity. Let's unpack what this means. If we ever hope to find a unified theory of everything, one that connects the large-scale geometry of general relativity with the small-scale fluctuations of quantum mechanics, we need to study phenomena where both are inescapably relevant. Black holes sit exactly in that overlap. But the chaotic details of matter-based black holes make clean calculations nearly impossible. With Kugelblitzes, however, the initial conditions are knowable. Light, being fully characterized by frequency, polarization, coherence, and intensity, can be modeled precisely. This allows theorists to simulate how such a system would behave as it collapses, not just classically, but quantum mechanically. It becomes easier to track how quantum fields interact with curved spacetime, how virtual particles emerge near the horizon, and how entropy is encoded. One major area of focus is the black hole information paradox. If a Kugelblitz evaporates, where does the information go? If it came from light, which we can fully characterize before collapse, then tracking that information becomes a testbed for theories like string theory, loop quantum gravity, and the holographic principle. The holographic principle, in particular, finds a beautiful expression here. It suggests that the information contained within a volume of space can be encoded on its boundary, like a 3D image stored on a 2D surface. In the case of a Kugelblitz, the idea that light-based information could be compressed into the event horizon and then released again through Hawking radiation is more than just poetic, it's testable in principle. It offers a way to check whether quantum unitarity, the conservation of information, holds up in the most extreme situations. Moreover, Kugelblitzes could push the conversation around quantum spacetime itself. At the Planck scale, unimaginably small distances where quantum fluctuations of spacetime dominate, the fabric of reality may not be smooth, but foamy, jittery, fluctuating wildly. A Kugelblitz that shrinks toward this scale through evaporation becomes a probe of this domain. It doesn't just curve spacetime, it dives into its deepest structure. And at that level, gravity and quantum effects can no longer be separated. Some physicists believe that studying the theoretical dynamics of a shrinking Kugelblitz could reveal how spacetime quantizes. Does the event horizon pixelate? Does evaporation stop at some minimal scale? Does gravity become repulsive at ultra-high energy densities, preventing a full collapse into a singularity? These are the types of questions that a quantum theory of gravity must answer. And Kugelblitzes help us pose them in the clearest possible terms. On another front, some researchers propose using entanglement entropy, the measurement of quantum information spread across space, to describe the interior of black holes. A Kugelblitz, created from controlled photons with known entanglement, could theoretically allow models of how entanglement becomes geometry, how the interior of a black hole emerges from correlations on the surface. This is deep, strange physics, bordering on the philosophical, but it's becoming more grounded thanks to tools from quantum computing and information theory. Even in practical terms, if we could simulate a miniature Kugelblitz in high-energy labs or in quantum field simulations, we could begin to test predictions of various quantum gravity candidates. How do gravitons behave near an evaporating horizon? Does supersymmetry emerge? Do extra dimensions, predicted by string theory, have measurable effects? In this light, kugelblitzes aren't just exotic constructs, they are gateways. They sit at the intersection of energy, entropy, geometry, and information. They challenge us to rethink what light can become, what space can hold, and what the universe permits. And perhaps, just perhaps, by studying them, simulating them, dreaming of them, we may finally arrive at the holy grail of physics, a single framework that unites the forces of nature into one elegant whole. A theory of everything, born not in the ashes of a dying star, but in the brilliance of light itself. In the vast and often paradoxical realm of theoretical physics, two of the most extreme and mysterious entities that have ever been proposed are the Kugelblitz and the white hole. Both are born from the framework of Einstein's general relativity, and both seem to defy ordinary experience. Yet despite their conceptual closeness in the mathematical language of spacetime, they sit on opposite ends of reality, one swallowing all, the other repelling everything. And understanding the differences between them offers deep insights into the nature of time, causality, and the universe itself. To grasp this contrast, let's start with the Kugelblitz. As we've explored in previous discussions, a Kugelblitz is a black hole, but one not formed from matter collapsing in on itself. Instead, it forms purely from concentrated light or radiation. The idea is that if you could compress enough energy into a small enough space, even if that energy has no mass, the gravitational field would become so intense that it warps spacetime into a singularity. An event horizon forms, and not even light can escape. It behaves just like any other black hole, but with a unique origin, not destruction, but intensification of pure radiance. Now enter the white hole, a hypothetical cosmic twin to the black hole. Where a black hole is a region from which nothing can escape, a white hole is a region into which nothing can enter. It's the reverse in time of a black hole. While a black hole absorbs all light and matter that crosses its event horizon, a white hole is theorized to expel matter and energy, potentially from a singularity, but nothing can cross its boundary from the outside. In some sense, it is not a gravitational trap, it is a gravitational fountain. This immediately sets up the first major difference between the two: directionality. A Kugelblitz, like all black holes, is an inward-pointing phenomenon. It represents entropy, collapse, finality. Once something crosses the event horizon, it cannot return. A white hole, by contrast, is outward-pointing. It's like the Big Bang localized in space. Matter and radiation emerge from it, but nothing can penetrate back in. It behaves as if time is reversed at the horizon. This distinction leads to another contrast: causal accessibility. Black holes, including Kugelblitzes, are causally connected to the universe. They form from collapsing stars, or in the case of a Kugelblitz, from focused energy. You can in principle see them form, fall into them, and interact with them, though you wouldn't survive the fall. They are grounded in the physics we understand, even if some aspects remain mysterious. White holes, however, are causally disconnected. They cannot be formed by any known physical process in our universe. You can't throw matter into them to build one. Their formation would have to exist from the start, embedded in the initial conditions of the cosmos. They are like cosmic mirages that blast radiation and particles outward, but remain untouched by the external world. Now let's explore longevity and stability. Kugelblitzes, as gravitational entities, follow the well-established rules of general relativity and quantum mechanics. They can form, grow, evaporate through Hawking radiation, and influence their surroundings. The equations suggest they are stable, dangerous, yes, but self-consistent. White holes, on the other hand, are theoretically unstable. According to most models, they would be incredibly short-lived, instantly collapsing into black holes the moment they interact with any matter. In fact, some physicists argue that white holes can only exist in mathematical idealizations, perfect solutions to Einstein's equations that don't actually manifest in the real world. The moment a single speck of dust tries to fall into a white hole, the boundary conditions collapse, and the white hole either vanishes or transitions into a black hole. Another key difference is observability. We have observational evidence of black holes. We see stars orbiting invisible objects. We've photographed the shadows of supermassive black holes at the centers of galaxies. We detect gravitational waves from black hole collisions. Kugelblitzes, while not observed directly, fall within this observable paradigm. They would look and behave like any other black hole. White holes, in contrast, have never been observed, nor has any data hinted at their presence. They remain purely theoretical constructs, often appearing as solutions in speculative cosmologies. Some researchers have toyed with the idea that certain high-energy gamma-ray bursts might be linked to white hole activity, or that the Big Bang itself might be a white hole in disguise, an explosion of energy emerging from an unknowable source. But these are unproven and deeply controversial ideas. Now consider thermodynamics and entropy. Kugelblitzes, being black holes, adhere to the laws of black hole thermodynamics. They have entropy, proportional to the area of their event horizon. They have temperature. They evaporate. They obey time's arrow, entropy increases. White holes, being time-reversed black holes, challenge this. Their entropy flows backward. They eject order into the universe. This breaks with our intuitive and observed direction of time. If one were to truly exist, it would force a rethinking of the second law of thermodynamics. In essence, white holes defy the thermodynamic structure of reality, making them not just unlikely, but perhaps fundamentally forbidden. There's also a philosophical contrast worth noting. A kugelblitz is born from the mastery of energy. It's an example of how light, when pushed to its extreme, can become the ultimate expression of gravity. It speaks to the elegance and danger of precision, of concentration, of unity between electromagnetism and gravitation. It is the culmination of power focused inward, creating darkness from brilliance. The white hole is the opposite metaphor. It is creation without cause, ejection without source. A place where something comes from nothing we can interact with. It reflects the strangeness of cosmological origins, why there is something rather than nothing. It speaks to the unreachable, the unprovable, the perfect symmetry that the universe seems to flirt with but never fully embraces. And finally, there's the speculative intersection. Could a kugelblitz transform into a white hole? Some theories in quantum gravity suggest that what we call a black hole may eventually bounce, that the singularity at the center could be avoided through quantum effects, and after enough Hawking evaporation, the black hole could explode outward as a white hole. In this view, a kugelblitz might not end in silent evaporation, but in a sudden rebirth, light collapsing, and then being released again in a final act of cosmic symmetry. If true, it would mean that light does not just die into gravity. It reemerges, through a mirror darkly, into a new domain, a white hole burst from a kugelblitz heart. For now, this remains in the realm of deep theory. But the difference is clear. Kugelblitzes are realistic, potentially observable, constructible, explainable within known physics. White holes are mathematical ghosts, symmetrical echoes of reality, perhaps never meant to be more than equations on a chalkboard. One represents the collapse of energy into gravity. The other, the eruption of gravity into energy. Two sides of a coin the universe may never let us flip. If a black hole can be made from light, that is, if a kugelblitz can arise from the sheer intensity of focused radiation, then the next natural question becomes, does it matter what kind of light? Could different forms of radiation, different frequencies, energies, or even quantum states give rise to different flavors or types of kugelblitzes? Are all light-born black holes identical, or could the properties of their origin, wavelength, coherence, polarization, leave fingerprints on the final object? Could there be multiple types of kugelblitzes? At first glance, general relativity suggests not. According to the famous no-hair theorem, black holes are supposed to be remarkably simple. Once formed, a black hole can be fully described by just three observable properties: mass, charge, and spin. It doesn't matter whether it formed from a collapsing star, a mountain of antimatter, or an ocean of gamma rays. All that complexity vanishes behind the event horizon. The black hole, in theory, forgets everything except those three numbers. This means that, traditionally, a black hole formed from red light and one formed from X-rays, if their total energies are equal and if all other properties are the same, would be indistinguishable. But here's where things get interesting. That principle applies once the black hole is formed and settled. But before that, during the actual formation process, and potentially at the quantum scale, the type of radiation used might indeed influence the black hole's behavior, or at least leave subtle traces that could affect how it evolves. Let's dig into the possibilities. First, consider the frequency of radiation. Light is not one monolithic thing. It exists on a spectrum, from low-frequency radio waves, to microwaves, to infrared, visible light, ultraviolet, X-rays, and up to ultra-energetic gamma rays. Each carries photons, packets of energy, but the energy of an individual photon increases with frequency. So while red light carries relatively low-energy photons, gamma rays carry incredibly energetic ones. Now, if you're trying to create a Kugelblitz, you have two variables to control: total energy and energy density. The total energy is the sum of all photons' energies focused on a single point. But the energy density, how tightly packed that energy is in space and time, depends both on intensity and wavelength. Shorter wavelengths, like gamma rays, can be focused into smaller spatial regions because they don't diffract as easily. This gives them an edge when trying to reach the critical energy density threshold to form a black hole. So in practice, if you wanted to create a Kugelblitz, you'd likely favor high-frequency radiation, not just because each photon carries more energy, but because it can be compressed more tightly. Does this mean a gamma-ray Kugelblitz would be somehow different than one made from visible light? Maybe, if you zoom in far enough. Here's where quantum effects come into play. The field of quantum gravity is still in development, but some theories suggest that the information encoded in the original photons, their quantum states, polarizations, entanglement relationships, may subtly affect the structure of the event horizon or the pattern of Hawking radiation later emitted. This leads to a speculative but fascinating possibility, that Kugelblitzes retain a memory of the radiation that birthed them, not accessible through classical means, but embedded in their quantum structure. This idea connects with the broader black hole information paradox. If black holes do somehow preserve the information of what went into them, as quantum mechanics demands, then the type of light used to form a Kugelblitz could influence its evaporation signature, perhaps producing different radiation spectra as it evaporates. Now, consider not just frequency, but polarization and coherence. Photons can be polarized. Their electromagnetic fields oscillate in specific directions. If you created a Kugelblitz from perfectly circularly polarized light, would it impart a specific angular momentum to the resulting black hole? Could linear polarization cause an anisotropic, directionally biased formation process? Could these effects persist, making one Kugelblitz spin differently than another? Again, classical theory says no. Once formed, it's just mass, charge, and spin. But in a quantum context, the initial field structure might encode subtle, short-lived asymmetries. And those could matter, especially in high-precision models of Hawking radiation, where even tiny fluctuations could affect information flow. Then there's the idea of coherence. Lasers, for instance, are made of coherent light, all photons moving in lockstep, with the same phase and frequency. If a Kugelblitz were formed from coherent radiation, would it behave differently from one made of a chaotic thermal mix, like the radiation from a star? Could phase relationships among photons lead to unique interference patterns during collapse, altering the formation dynamics? These are still open questions, deep in the realm of theoretical physics, but gaining traction thanks to advances in quantum optics, computational models, and analog black hole simulations. Some proposals even suggest building synthetic analogs of Kugelblitzes using different light profiles to see how the collapse thresholds shift based on frequency and coherence. Now let's get even more exotic. What if, instead of just visible or gamma radiation, you use neutrino radiation, gravitational waves, or hypothetical particles like axions or dark photons? While these are not forms of light in the traditional sense, they carry energy. If focused tightly enough, hypothetically, could they form non-electromagnetic kugelblitzes? If so, we might enter a new class of objects, non-photonic kugelblitzes. These would be formed not from electromagnetic radiation, but from other quantum fields, perhaps even dark matter or exotic scalar fields. Their gravitational behavior would likely be indistinguishable from a normal black hole, but their origin and decay pathways could vary, offering windows into hidden sectors of physics. This leads to the tantalizing possibility that in the early universe, multiple types of kugelblitzes could have formed, some from electromagnetic radiation, others from decaying inflationary fields, primordial neutrino baths, or even pre-quantum fluctuations in spacetime itself. And these different origins might influence how these black holes evolved, evaporated, or seeded galaxy formation. In speculative models of advanced civilizations, there may be even more diversity. Imagine engineering special-purpose kugelblitzes, one formed from blue light for rapid decay and high radiation output, another from tightly focused X-rays for compact storage and long lifespan. Perhaps each type has a role, one as a starship engine, another as an energy sink, a third as a data destructor or information vault. So, are there multiple types of kugelblitzes? In classical physics, no, once formed, a black hole is a black hole. But in quantum physics, formation theory, and advanced applications, the answer is, very possibly yes. There could be spectral kugelblitzes, polarized variants, coherent space types, and non-photonic cousins. Each subtly different, each revealing new layers of how energy and spacetime dance. And as we explore further, through theory, simulation, or maybe even one day an experiment, we may find that the diversity of light doesn't end at the rainbow. It may reach all the way into the event horizon. In the grand theater of the cosmos, few transformations are as paradoxical and hauntingly poetic as the creation of a kugelblitz. The moment when pure light, the very symbol of clarity, knowledge, and life, collapses into an abyss of absolute darkness. Here lies a transformation that borders on the mythical, illumination becoming oblivion, the brightest thing in the universe giving birth to the darkest. Philosophically, it stirs something deep, something primal, a confrontation not just with physics, but with the symbolism that has guided human thought for millennia. Light has always been more than just electromagnetic radiation to us. It has been metaphor. Civilization, from its earliest myths to its most refined philosophies, has revered light as a representation of consciousness, hope, understanding. We speak of the light of truth, the light at the end of the tunnel, the inner light of being. To see is to know. To be enlightened is to be awakened. Darkness, in contrast, is what we flee. It represents the unknown, the unseen, the feared and forgotten. So when science tells us that light, concentrated beyond imagination, can collapse into a singularity, it cuts deeper than a scientific curiosity. It challenges our deepest metaphors. It whispers that even light, in its purest, most perfect form, contains the potential for erasure. That brilliance, unbounded and unchecked, becomes consumption. The very agent of revelation becomes the engine of concealment. In this, the kugelblitz is more than a physics concept. It is a parable. Imagine, in a metaphysical sense, that understanding itself grows so intense, so all-consuming, that it folds in on itself, becoming impenetrable, a mystery too dense to shine through. This is the paradox of the black hole. The more mass or energy you gather, the more you know about a system, the less you can actually see. At a certain point, knowledge occludes itself. Perspective collapses. Curiosity, unchecked, becomes singularity. There's also irony in the fact that to create a kugelblitz, one must master light completely, focus it with such surgical perfection, control it with such mathematical precision, only to watch it die into absolute disorder. This is not entropy born of chaos. This is entropy born of symmetry. We focus the most structured thing, the laser beam, the monochromatic pulse, the coherent field, and it gives birth to the ultimate structureless state, the black hole, where all distinctions vanish. From a philosophical lens, it suggests that order pushed too far becomes indistinguishable from disorder. Light, when dispersed, creates vision, contrast, color, perspective. But compress it endlessly, and it becomes nothingness. No photon escapes. No image forms. It is the antithesis of perception. And yet there's beauty in this collapse. To think that something as intangible as light can bend the very stage of existence, space-time, into knots. That photons, which have no rest mass, can summon gravity so powerful that it warps the fabric of the universe. It's as if the ephemeral has teeth, the intangible has mass, the invisible has consequence. This gives weight to things we thought weightless. It suggests that even the softest notes in nature's symphony can shake its foundations. In a way, the Kugelblitz reminds us that nothing is as simple as it seems. That light, which we once believed to be the opposite of gravity, weightless, airy, free, is in fact its servant, its architect, even its origin. That gravity is not reserved for heavy things, but for concentrated truths. It also whispers something subtle about our place in the universe. We often associate light with human endeavor, discovery, science, enlightenment, progress. The laser is the pinnacle of that journey, the beam of coherent understanding. But the Kugelblitz says, beware. Because sometimes, in our hunger to understand, we may stumble upon truths so dense they cannot be undone. Knowledge that collapses into blackness. Tools that build oblivion. Answers that erase the questioner. There's something unsettling in knowing that if we ever manage to build a Kugelblitz, it will be through perfect alignment, flawless symmetry, and complete control of our most advanced technologies. And the reward? An object that defies observation, devours information, and ends inquiry. The prize of total precision may be the death of distinction. It is the ultimate reminder that the universe is not obliged to reflect our symbols. That light, no matter how sacred we hold it, is governed by the same laws as everything else. That our metaphors, of good and evil, of clarity and confusion, break down at the event horizon. That the cosmos is under no obligation to honor our poetry. And yet, it does. Because in the story of the Kugelblitz, there is a strange, inverted poetry. A kind of cosmic haiku written in photons and gravity. From brilliance born, light folds upon itself. Darkness shines. Perhaps that's what makes the Kugelblitz so deeply compelling, not just as a scientific concept, but as a human one. It is not just a black hole made of light. It is a mirror held up to our brightest dreams, revealing the shadows they cast when pushed too far. We live in a universe where light can become darkness. And in that paradox, terrible, beautiful, humbling, we glimpse the sublime. In the end, perhaps the most haunting truth of the Kugelblitz is not the mechanics behind its formation or the physics of its existence, but the quiet poetry it inscribes upon the canvas of the cosmos. For what is a black hole born of brilliance, if not the universe reminding us, once again, that every extreme folds into its opposite? We tend to think in binaries, light and dark, mass and energy, creation and destruction. But the Kugelblitz obliterates those neat compartments. It shows us that when you take light, the emblem of freedom, velocity, weightlessness, and push it to its absolute limit, it becomes gravity, stillness, imprisonment. It becomes the very thing that traps light itself. And not through decay, but through perfection. Not through chaos, but symmetry. Not by breaking apart, but by drawing in. This is not destruction. It's concentration. From photons dancing across the void, flickering, vibrating, massless and carefree, emerges the most fearsome object in the universe. A thing with no surface, no texture, no color. A shadow so absolute, not even time can crawl past its edge. And yet, its origin is not doom, it is discipline. Focused, radiant, unrelenting discipline. This collapse of light into darkness is more than physical. It is metaphor, myth, and mystery combined. It is the story of limits, of how even the most sublime forces become monstrous when taken too far. It is a story not just of energy, but of elegance. A whisper that brilliance, when narrowed into a single point, becomes silence. And still, even in that silence, something persists. Hawking's work suggests that even Kugelblitzes, even the most austere black holes, may shimmer faintly at the edge, shedding particles into the void. A slow unraveling. A gentle radiation that hints at rebirth. So perhaps, in time, the light that vanished might return, not in the form it came, but in echoes, in quantum sparks, in the soft leakage of information that once blazed. Perhaps the universe is not merely a machine of collapse and consumption, but a great recycler of radiance. Perhaps every black hole, no matter how it is born, from dying stars or laser beams or the roiling plasma of the early universe, is part of a larger narrative. One that curves, bends, and folds light in ways we're only beginning to understand. To study a Kugelblitz is to flirt with the edge of comprehension. It's to gaze into a possibility where our most trusted assumptions, about what makes a black hole, about the nature of mass, about the limitations of energy, are not destroyed, but reimagined. And in that reimagining, we glimpse something beautiful, that the cosmos doesn't think in terms of opposites. It thinks in curves, in convergences, in moments where the difference between light and gravity, between motion and rest, between brilliance and shadow, becomes irrelevant. Because at the most fundamental level, what is a black hole, even a Kugelblitz, if not a place where meanings collapse? Where space-time folds, where equations diverge, and where metaphor meets mathematics in the most literal of ways. We came seeking understanding. We found contradiction. We sought the ultimate brightness. We found the perfect black. But that is the lesson of the Kugelblitz. That from light came darkness, not from destruction, but from concentration. The universe, once again, blurs the line between opposites. And in that blurred line, we see the signature of a cosmos that is not just physical, but poetic. Not just real, but wondrous. A black hole born of brilliance. A shadow born of light. And us, ever reaching, ever wondering, drawn toward the event horizon of knowledge itself. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.